many, like 2,000, two,
To kilowatts.
yeah, kilowatts. And then it shows you what it is. Cause it's gonna say how many kilowatts, and all of them are right here. They ain't gonna go higher than this. So that one is gonna be easy.
Okay.
And then,
So that's the answer already there?
yeah, the answer
So you
right
don't
there.
need to
So you don't need to calculate nothing.
that's,
Yeah.
Okay.
So that was,
You
that's a good one.
can put this one,
In the, somewhere, I don't know where, like maybe I'm gonna try to put it somewhere.
but you know, he look at that, you put this one in the gate,
I'll
take
put
in
it-
your book, you know?
Yeah, I think I'm gonna put it somewhere like,
But you need to be careful because I see it, when you put this one in the book.
maybe it needs to be black and white.
Okay.
Make a copy, I don't think probably make a copy, then it'll be black and white. Put it in the back with the charts, you know? Like somewhere
I
like,
like it. I like it.
yeah, somewhere back here,
Yeah,
like,
yeah. So whatever you need.
Yeah, whatever, yeah, yeah.
Yeah.
yeah, put it with the table.
Okay, and put it like that, look like it.
Yeah, that's what I'm gonna do. I'm gonna make a copy, black and white.
So
it won't
this
cut me.
orange, that you talking this morning?
No, I just seen it. We talked about, he did calculation for the range, but when he did the calculation, this is what it is. That's what it is. So these are some pretty good, this is some pretty good information. So then,
Maybe saying this, what is that?
that one's for
Range.
one, just single.
Just one, and the multiple.
Multiple. Yeah. Yeah. But he was saying something about this one too, though.
You know,
I think it was, yes, something about on this one too for the parts. For the part, for chapter 3, the wiring method part. I gotta go over that one. But it's some good information. He's saying some good information.
Who's that for? No back.
this is,
What's that?
this is the Nemo, or is it?
I'm Jason Novak.
No,
Name somewhere.
this is for the chapter 3.
Oh, who knows? I've got in trouble.
I know, I'm talking about the.
I think it's been on
And, I think the size, I'm not sure, but I know it's gonna be helpful. But I figured out too.
Oh, yeah.
What's your
Yeah, the government require me to do like, so I have a LinkedIn, I don't do it, I don't do it.
Yeah.
The government should require to have, you're supposed to have a social media account and a website, so they can
Marcus.
review you.
Yeah. Mark.
So yeah, I'm on, LinkedIn.
Okay. Photographs.
Yeah, and it's, so I don't know that,
Mark.
but,
Marcus.
you go-
Oh, right there. That's my name. Yeah.
And then we just did a, we did a startup company.
Yeah,
called,
yeah,
PAT.
that 30 bucks.
So that one
Yeah,
is a,
yeah.
a branch off of all that
What are you thinking about?
to do, basically grid technologies. And I'm the vice president of technology for that company.
I know.
So you know when we're in the garage, we get to like just invest in some shit. This old man like just allowed me to do that so that we can try, cause you know like renewables and grid, they fucking don't like each other. So I'm trying to create some technologies and create some inventions. We have patents, we have one patent right now.
Yeah, it's hard when you get to the thing, you have a family.
Basically solve all renewables. So it's not just the state, we're fucking bad. We're the solar panels. So the sun comes out, boom, there's production, starts pushing the grid, right? So we're trying to create some technologies that get placed in power plants, switch stations, switch yards, all the infrastructure across the United States to help reduce that a little bit. So, and some other shit too.
It's hard like this.
Oh, it's hard. That's my right there.
Everyone knows Bitcoin.
I did it like that when I take my journeyman test.
No, I can do
I did
that.
it like that.
I like that, I like
No
that.
chain
Like
that's
that.
or is some.
If I did my
She can do
journeyman,
it
like
like
that
that.
hard,
A
yeah.
lot of it is like
Yeah, when I did my journeyman test, I did my test like that. I didn't know, I didn't read the instructions. I just thought it was gonna be easier for me.
Load bank that makes money, but they don't need the energy. So, the energy and she backed them, and then
She
we
did it
used
for people
the
that
money
see
making
me,
thing we were doing
and
with
she
that.
said, "Ah,
Because if you look at the miners, all the miners are like 5,000
But I
watts.
tell him, poor
Call
guy, I got one.
because
Before that,
so they had tens of thousands of these things running, and had 5,000 watts.
How comes this morning?
But the thing what's cool about them is that with a computer, you can be like, hey, I'm running on 5,000 watts, but if you need to curtail back, you can actually run it down to 1 watt. It'd still be on and running without having to shut it down and do like a restart. So you have,
No, I'm looking, you know what?
5,000 watts, or call it 5 megawatts.
That's what I'm saying.
Well, we don't have to turn off the miners. Let's just say we were making $10,000 a day, then we could
But nobody's here saying
back like a peaker plant.
Yeah, the
And
structure,
then you
man,
have to
that's
spin up a
the
peaker
structure.
plant and be running a bunch of fuel, right, to start the peaker plant.
Yeah.
So we were taking a miner.
I would say my only look is, hey, look at that.
And
When he
then
says something, look at me.
basically
Because
converting
you
them
don't
into
pop.
peaker plants.
Yeah.
So we're making X.
Yeah.
And
No, no.
then, hey, if you need the money, we have to raise it with the utility, and then like, hey, then buy it for more than we're making
Yeah.
in the time that they need that peaker plant.
No, no.
And you don't
I-
have to
I-
pay
I looked at it, I
No,
read
you can take it out now, that's, it's too late.
So you just curtail them back.
No, it's
You
not.
give them that extra power at that moment they need it, and then whenever it's done, you
Better
just take
sell
that back.
it, better sell it, because, no, why did it this morning?
Dogecoin and Bitcoin.
She put it down, look at that, that's my first time she put that. Look at you, really.
Yeah, it's hard like that.
Yeah, like Bitcoin mining.
You got.
Everybody knows Bitcoin mining, but so I'm just an electrician.
They charge $20 a
We
day?
all tear shit apart.
maybe
We should get shit.
Cut it, and let them tap it.
So I had one running at my house.
Hey, 'cause they, have you seen, look at, they do it,
Yeah.
they do a good job. Cause last time I let them tap it, when I was
That might be better.
Cheap.
Cut the tab.
Yeah.
So what I realized
Yeah.
quickly is I attached some electronics to it. We have a guy, his son.
So, looks nice, no one.
Kids.
Looks nice,
Gets
no
a
one.
hoodie, fucking doing
He
this
wild,
shit.
he wild, he sell
He's like a coder
book
guy.
with the
So I had him put
Yeah, they do.
software.
But yeah, but it's kind of.
Some hardware that I built.
That's just-
Maybe I did a lot of like down to circuitry level stuff. So
No, it's 200
resistors,
something.
Nah, it ain't.
you know, resistors, transistors.
It's 600, 650, you buy it.
Each other, whatever.
Flux of
Yeah,
that.
yeah, so.
But the book is
So
250.
I could attach it to that, so like essentially take every 200 amp panel that I was back feeding, I was actually pulling from some stuff from my house.
It's gonna be good, because like this
Brand
one,
new
but
400 amp
it's
upgrade
bad.
and a
No.
half. And I was pulling 300 amps continuous use
Yeah.
all year round, my electric.
But then you
Sometimes
also
the
look
page,
at
sometimes the pages be
He's gonna use it,
Well,
but I think return because I passed 10 days for 10
Listen to be okay.
You're sure, he's no missing, no
When they
missing
needed
nothing,
power, I was able to
a page,
computer by
you check out, okay, I got it.
I was like,
and I was
Oh,
able
yeah.
to
2017.
tail back my
Okay.
system. Almost, let's say like 380
But I gotta make sure I buy them new though.
down to like.
This one,
Yeah, cause sometimes I
Just
ain't
the
gonna
house,
buy
right?
you.
You know, the air conditioners didn't need.
That's come on.
I was able.
no, I buy another place,
No,
but.
see, I like
Look
That's
at that
that
shit.
disruption to the grid, right?
Yeah, cause
I can
one of my
read
You
it.
have to start back up, bring back on, bring up.
I can read it, but that's-
Came on that?
Interrupting, too much power or not enough power to it.
2017.
Basically, it's totally, yeah, exactly, so on an electric system,
Yeah, my
that was
2017.
the old man, he's 84, this guy,
Came out.
fucking
It
84.
was like, it was okay until I started really using it. But then the
Got
food started
mine.
coming out.
I still got it right today.
John Billingsley is a guy I worked for, older guy, I mean, he was here in the Dust Bowl, like, he didn't have electricity on his farm.
So,
His dad was a farmer, but his dad on the
here's
weekends.
the.
Yeah, that's the secret
And then
too.
his dad would grab him
Here?
when the power poles.
That's my big
He
twin.
was
Right here.
he's out for lunch.
All this section. Look at that guy. He know because he get before.
30.
Even the one from this guy said,
This is like.
Every time I go by a farm,
This one.
you bring down from a transformer, 240 go to 60.
so I pay for that. I don't know if you're talking there. That's what I'm saying.
And if you have a question, and if you have a question.
That area. He's seen it all.
He didn't want that.
He started out, he like,
But I need another class for understand that. Hey, yeah.
so he like us, he gonna work until he's dead. I thought the same thing, but I'm like 3 times as hard at work, and now it's never, it seems like it's never. 3 times hard work, continuous use. Continuous use. Yeah, until I'm.
Hey, you know, they took that out too, for continuous duty, they don't have it.
You know, call again?
You got 3 hours or more.
You got some milk
They have
for you.
continuous,
Yeah, you-
continuous,
yeah,
load.
Yeah.
Crazy enough.
And the day
Hey, keep on coming.
Used to be 3 hours or more. 3 hours. Yeah.
Now you're gonna make me look at it.
Yeah.
Y'all had,
Click under continuous load, that's what you're
scale like it's scale.
Since you're bringing it up, and you're talking about it, we might as well talk about that real fast, so I don't forget. You know, the one thing that, you know, this entire code book is written around is basically heat's the biggest enemy of electrician. It really is. I mean, everything that we do in this code book is practically, like a couple of things for over voltage, right? Which is kind of a newer approach, but I mean, traditionally, this code book's always been about, you know, protecting property and people against fire, really, you know. Heat's always been our enemy. It creates resistance, right? The higher the resistance, the more heat it's created to push electricity through the same amount of wire even. So it's almost like it builds on itself sometimes. And if you think about the one thing that is, you know, constant with everything that we do, it's wire. I mean, if you think about what we really are, we're wiremen.
Copper, baby.
Copper or aluminum, if you.
Not enough money in aluminum, sorry.
But the point about it is that, you know, anytime we introduce heat into our circuit, we either have to oversize our conductors, to kind of compensate for it or deal with somehow or another. And so heat being a problem, our number one problem, continuous duty is kind of how we describe that problem. And so he brought up a point on page 34. You know, there's a continuous duty, continuous loads, and continuous part. Basically, a continuous duty is any cycle that hits its maximum capacity across any given point. Continuous duty, actually under duty, comma, continuous, I think is where you find that one, which is on page 36. So if you look on page 36, continuous duty is technically described as operation at a substantial constant load for indefinitely long time, right? So that's the first part. But if you look at on page 36, bottom left-hand side under continuous duty, duty, comma, continuous. Remember, duty is a period of time that we expect a conductor to have some sort of a stress or some sort of demand put on it. So continuous duty specifically means operating a consistent load for indefinitely long time. And if you look at continuous loads, which are on page 34, continuous loads are listed as a load where the maximum current is expected to continue for 3 hours or more. So continuous loads, in this case, when we're talking about the heat value, at 3 hours, we really put a lot of stress on that conductor because it takes a lot of energy to dislodge an electrode and bump it over to the next molecule and back and forth and back and forth. And you do that to a conductor over and over again, after about 3 hours, it's gonna get warmer than it was originally, right?
Breakdown.
Just, it will break down for sure, but that heat value is what we are trying to describe here. So at 3 hours, we figured that back and forth has built up enough resistance that it's gonna start creating even more heat. And so that's really what we're trying to protect here. Anywhere in the code book that you see these items, we're talking about 3 hours plus, so 3 hours being the beginning, okay? Anything longer than that, 125%. Under continuous loads.
34. Page
Page 34, left-hand side.
We use the term continuous duty kind of loosely, but when we're talking about continuous loads is really what we're
I
describing.
didn't even see the duty in
So the continuous loads being 3 hours or longer, the heat value, what we're gonna do is we're gonna use 125% as a factor. So it's just like when we derate things in other cases, in this case, we're increasing it, but it's still a factor, right? It's just a consideration that we have to multiply or to take into account. And what happens here is we're gonna take a 25% increase on the load value, thereby forcing ourselves to put a bigger wire on it, right? Because the load's gonna look bigger. And so at the end of 3 hours, if we were to put a meter on there, hopefully that 25% bump will give us a large enough wire that it won't be a problem anymore. So if we had a load that was rated for 100 amps, that was non-continuous, I have a 100 amp breaker and a wire size is number 3.
3.
Is that good for 100 amps? Number 3?
Sounds right.
I think so. 3 is good for 100 amps, I think 2 is good for 115. 130.
What's that for you?
That's number 3. And a 100 amp breaker, right? OCPD, overcurrent protection device. So all that's fine, as long as these loads aren't continuous, right? That's the problem. If I had 100 amps that was continuous loads, then I'd really have 125 amps worth of load that I'd have to deal with, because I'd take a factor of 125%, times it times 1.25 on your calculator. So really what my load then would be is 125 amps, thereby forcing me to put a number 1 instead of number 3. So 2 sizes larger conductor. And what's that breaker? Did you
It was 125.
So we have 125 breakers. And instead of number 3, now we're at number 1. Did you see what happened? Right? So 125%. Now a lot of times in the code book, what you'll see is they'll come from the other side. In other words, switches, breakers, things that are not rated for continuous duty loads at their nameplate or their straight nameplate load value. This breaker here that I put at 100 amps is not rated for continuous duty loads, right? So what you'll see, the reverse of that 1.25 or the reciprocal math of that is 80%. And so a lot of times in the code book, instead of 125, they're going to just talk about using 80% as a derating factor to take an equipment that's not rated for continuous duty and lower the value of it so that it is then equal to what the continuous duty load increase would have been. But it's one or the other. For example, let's say that I had a 20 amp breaker, right? 20 amp breaker at 80% of a load gives you how many amps?
16.
How many guys, have y'all heard that before?
Yeah.
Right? Is that every time?
No.
Let me tell you, they wouldn't make a 20 amp breaker if I couldn't put 20 amps on it, right? I mean, if they didn't want me to put 16 amps on it, they'd put it 16 amp rated breaker, right? 20 amp rated breaker will handle 20 amps. What it won't handle is 20 amps at 3 hours or longer, right? And so if I were to take a load that I knew was 16 amps and I knew that was gonna be operational for 3 hours or longer, to increase that load, I'd use a factor of 1.25, and what's 16 amps times 1.25? 20 amps, right?
20 amps.
It's the same thing,
25 amp breaker on there?
20 amps.
Or 20 amp?
So 125 and 80 are the exact same thing. One goes one side of the equation, the other one goes on the other side of the equation. In the code book, because they don't really know exactly what you're installing, they almost always have to use the 80% rating. So you'll see that, for example, what's a good example? Motor disconnects or motor controllers. 430 dot page. Hold on one second here. Page 357. 430.109C. Page 357. So I'm at 430.109C, it's at the bottom left-hand corner of page 357, 430.109C. Look at number 2 and the way it's worded. On an AC circuit, a general use snap switch suitable for use only on AC, not a general use AC, DC snap switch, where the motor full load current rating is not more than 80% of the ampere rating of the switch. They're telling us this because that switch is not rated for continuous duty, but the motor is continuous duty load, right? So if I had a 20 amp rated switch, because it's not rated for 20 amps of continuous duty, I'd have to derate that switch, meaning the biggest motor load that I could put on there would be 16 amps, make sense? But really, that 16 amp motor that's 125% continuous duty would have a load that looks like 20 amps from our side, right? So I want you to be careful with that 80% because a lot of times we get confused and used to that and think, okay, well, that's always the case if we do it with a 20 amp breaker. It's not. It's just where the breaker's not rated for continuous duty and I've got continuous duty loads. So I have to do one of the two things. I either have to take the load value and increase it by bumping it up, or I have to take the breaker and dumb it down so that I take that consideration into account. One way or the other, but I don't do both, right? You'll see that back and forth. I think the code book almost always has to come from, you know, the other side, because they don't really, I mean, there's just so many things you could do, but.
For example, motors and engine, what is an example?
Solar.
Continuous duty? Pretty much any commercial, yeah.
It's
lights
always
and-
been told lights,
Hmm?
lights,
Yeah.
what always been told.
There's an exception to that now. The lighting table that we have has continuous duty already kind of factored into it, so there's, I don't want to say that just flat out anymore, but signs or commercial lighting of any sort. In fact, I think it would be almost hard for them to tell you that it wouldn't be continuous duty if it was something like commercial lighting, because I mean, there's just no
Once
way.
it goes on, it goes on.
Yeah.
It's all there.
12 hours on average, I guess,
Yeah,
right?
yeah.
So, I really don't see how they could tell you, for example, the lighting load in this room here, right? I would have to factor this as continuous duty lighting, because I know that at one point, there's gonna be a 3-hour, operation in here, and it's gonna be on for 3 hours.
I'm finding the same thing in the solar world for all the backfeeding breakers, same thing
Yeah.
there too.
Yeah, there's some fuzzy math in there with some of that, but yeah.
There is.
But they use 125%, I think, for that same. for
Well, I
that
came into
breaker.
this group with always popping a breaker, always, or fuse disconnects. It always rate real close to that fuse disconnect, what it is usually a 30 amp or a 60 amp.
Mhm.
Always popping, everything else is correct, but
That makes sense, cause you're gonna be backfeeding it all day long. Yeah.
as soon as the sun's out.
Yeah. But again, at the core of all this, we're talking about the heat that's on that conductor, right?
Yeah.
And so, again, the breaker's kind of a relative afterthought, because we're really talking about the wire itself and the conditions of use that we put on that wire, and so it's the load that we're trying to increase to make the wire bigger, so we don't put as much stress on that conductor. All right, so let's go back to what we were gonna start with, and that is grounding and bonding. Wanna make sure that we have time to go through that pretty comfortably and get through, the tables that are here. 250, if you look at your code book, starts on page 137. In your textbook, I want you to turn to page, page 143, I guess. Yeah, we start on page 41, it's written in your textbook, but there's a diagram that you see on page 43 that I think is pretty nice to kind of keep handy. And then your code book on page 137. Grounding and bonding, I tell you, you'd think that we would understand grounding and bonding really well, because I mean, it's been a staple of our career for forever. I think, I will tell, one thing I'll tell you about Mike Holt is that he really, when he really puts his mind into something, he won't let go until he just worries it to death, It's not a bad thing, but, he got into the grounding and bonding stuff, especially swimming pools and he hadn't let it go. I mean, he said. But, he's made some instrumental, pushes in our industry to make us understand, because, I've always thought of ground as being a strict expunge, right? I mean, we just dump current in the ground all the time, and we think, all right, well, it's just gonna go away, right?
No.
It doesn't go away. In fact, it will sit there and wait for a way to get back to its original source. When we derive a neutral or ground at a service point, that derived neutral point is where our ground source is trying to get back to any of your line current or your neutral current, it's always trying to get back to that derived point. And so if you were to dump that in the middle of a branch circuit or in the middle of a distribution, anything that's metallic in between where you dumped it and that derived neutral, it's gonna try to find its way back, and it's gonna use any pathway it can. And so we've really, I think, come a long way from understanding kind of how we deal with stuff. Now, we do use the earth as a sponge for some grounding, right? And so the way you wanna look at this is basically, in my head, I've got three different buckets, I guess, if you will. I've got, let's call it earthy, because that will help you kind of keep it separate from, grounding and bonding when it comes to branch circuit stuff. So the only time we really use earth like a sponge is at the service where we've got an over voltage condition. Occasionally, I don't know if you guys have ever had a TV get burned out because of a lightning storm. Did y'all ever had that happen? Yeah.
Show your age.
Hey, where you have conditions where you've got lightning or over voltage that might hit a system, you really wanna have a way for that over voltage to come through your service on the outside of any overcurrent device and make its way to earth, right? So it's kinda like a shunt, if you will, I guess. This is called your grounding electrode conductor, or your GEC system, right? I might refer to it as my earthing system, just so that I don't get confused. But its purpose is to keep that over voltage outside of our system so it doesn't backfeed into your distribution. Because remember, all of your grounded stuff in here is all bonded together. So if it doesn't have a good pathway here, guess where it's gonna try to go?
Through all your branch circuits.
Yeah, your TVs.
Everything,
Yeah. I don't know if you guys ever heard that old wives' tale, and it's actually not an old wives' tale. The lady on the phone where it's lightning on the outside and the phone rings, so she picks it up and electrocutes her. Y'all ever heard that before? There's this website called Snoops or something like that, where you can Google, not Google, but you fact check things like that. Have y'all ever heard of that? Snoops.com or something, I don't remember what it was. That actually happens, like 2 or 3 people a year get killed by a straight volt. Yeah, going back fed into the system, not necessarily the phone, but I thought that was pretty fun.
really stop?
Huh?
So, surge protector.
Surge protectors help quite a bit, absolutely, yeah.
They're not save all, but they help, yeah.
This table is 250.66, and it is on page. Thanks, sir. Page 149. And I want you to write on the top of this table in great big chief handwriting, GEC, maybe even write the word service, so that you remember the purpose of this table is the earthing system or the service. We're trying to base this conductor outside of any overcurrent device. So in other words, it has to happen on the line side of any overcurrent device.
Grounding electric conductors?
The GEC.
And what page, sir?
Page 149. Page 149. The table is 250.66. I've just got the word service. And the one main thing you have to remember is this is based off of the single largest ungrounded conductor in the service. That's what this table is based off of. Now, a lot of times we run parallel sets, and it's what they're talking about with the equivalent area for parallel conductors. We'll talk about that in a second. But basically, if I go through an overcurrent device and I go past it this direction, I'm no longer talking about my GEC, and now I'm talking about my EGC section. So this is the service based off the table on 250.66. After I go through an overcurrent protective device or a breaker or fuse of any sort, then anything after that is referred to as an EGC, equipment grounding conductor. And you'll find that on table 250.122. Look at that really quick. That's on page. Thanks, sir. You were handy. I mean, the tables are very vastly different. Now, I'd say, for the journeyman, table 250.122 is far more important to you than the other table, and for the masters, vice versa. It's 250.66 is far more important for you guys, but either way, they're both important tables for us. So, on page 158, I want you to write on the top of that EGC and put branch circuit. once I go past an overcurrent device, then the ground conductor purpose is for it to carry that, that surge back to that overcurrent device. And so it's based off of the size of the overcurrent protected device ahead of it.
Do you say put branch circuit?
Branch.
Branch circuit,
EGC equipment, basically a branch circuit,
Equipment grounding.
equipment and personnel protection.
Yeah. Well, we got back so it can trip the breakers so that it doesn't go through you.
Absolutely, absolutely. Right? So this one is based off of the breaker ahead of it. The other one was based off the conductor, large single conductor in service. All right, let's go back to page 250.66, page 149. Now let's look at this table really quickly and kind of talk about how it works. The nice thing about the table 250.66 is this wire right here will never be required to be larger than a 3/0. That table ends at 3/0 as the biggest conductor. And so there is not really any way for, I mean, if I go over 1100 kcmil on my conductor, my single large conductor, I'm still at a 3/0. So if I had a 2000 kcmil single large conductor in the service, 3/0 would be the largest conductor, okay? So that's nice because it limits it to that section there. Now, what you want to be careful of is you'll notice copper is on the first column, aluminum is in the second column. If I'm dealing with an aluminum feeder, right, I'm going to be in the second column, but I may be on a different row with the same size equivalent for copper. For example, if I had a 250 kcmil copper conductor, a 250 kcmil copper would be what, the third row? Or the second row, which one is the third row?
250 would be third row.
Fourth row.
Fourth row.
Fourth row.
Is
The
it going
250 would be
over?
over a 3/0, right?
Oh, yeah,
Not
copper.
350.
Through 350, over 350 is 1 copper.
So a 250 kcmil copper conductor is my single largest service conductor, would give me a number 2 copper. Right?
Yeah.
No, 250 kcmil, right? So my service conductors, right, are 250 kcmil copper. So that puts me in that very first column, right?
Yeah.
So I'm gonna be on row 4 where it's over 3/0, but not larger than 350, right? So that puts me in number 2.
Yeah.
Right?
Number 2 copper.
Number 2 copper. What if I had a 250 kcmil aluminum?
That'd be a number 4 copper.
So be careful- Be careful with that one, because I mean, that's gonna put you in the second column, that'd be the third row instead of the fourth row, so we're up a row now, if you look in that second column. 4/0, 250.
You're number 2?
No, it'd be, well, 4 copper or 2.
Yeah, I'm gonna answer number 4, and the reason I'm gonna answer number 4 is, I always have to think and talk and express in terms of copper, right? And so, even though I've got an aluminum feeder, doesn't necessarily mean that I'm gonna answer in aluminum. I'm only gonna answer in aluminum if they specifically ask me for the answer to be in aluminum. Right? Be really careful of that, because they really do kind of play games with that. So, this aluminum feeder, it's pretty common. I mean, how many times you run aluminum feeders and then ran aluminum ground rod, or ground?
Nope.
Hardly ever, right? They
Yeah.
almost always use copper, do you not? So, I mean, that makes it
Yeah.
a fair scenario, right?
Yeah.
It just looks funny when you put it down on paper, but it, you know, it's not uncommon. All right. I was wondering why did they, what's bigger than the 3/0? 4/0, right? Does anybody in here know of any wire size bigger than 3/0, smaller than 4/0, that you can go buy at a standard electrical supply here in the US? No, right? It's 3/0, it's 4/0. I mean, after that, it goes into the 250, 300
kcmil
right?
stuff, yeah.
Why don't they just say, for God's sakes, 4/0 through 350?
There's some brainiac wanted to make it confusing.
Everybody understands that 3/0 copper would be the third row, right?
Right, I see what you're saying.
And the next wire size is 4/0, so it'd be 3/0, 4/0, right? So why don't they start the next row as 4/0? Well, here's the reason why. When we run parallel conductors, there's no magic to parallel, right? I mean, basically, if I have a large demand load, it's cheaper for me to run smaller sets of parallel copper conductors than it is to run one, because I don't really, we have what's called skin effect, and skin effect in AC basically pushes all of the electron flow to the outside edges of the conductor, right? And so there's a lot of the core that never really even gets used when you boil down to it. So the larger the wire we have, the more strands we try to put in it, so that we have more surface area, right, for that skin effect to work. But after a while, your wires still get so big that you just have some unusable material in that conductor that doesn't really get used. So if you look at, for example, a 500 kc mil conductor, 500 kc mil is good for 380, is that right? 500 kc mil is good for 380? Yeah.
380, just like 400.
All right, what's 1,000 kc mil then? Should be 760, right?
Well, it's not, that's like.
If I double the wire, why don't I double the ampacity? But I don't do it. What do I get for 1,000 kc mil in the same 75 column?
540.
540. So instead of getting 760, I get 540. So I doubled the amount of material in my feeder, and I got 40% of an increase in the ampacity.
Double the cost of price.
And labor on top of that, because it's twice as heavy. 1,000 kc mil copper, oh my God. I've only done that one time in my career, and that was enough. And it wasn't, I bet you it probably wasn't but 20 feet long either, and it whooped about 11 of us, right? It's really heavy. So at a certain point, it just makes no sense for us to run larger conductors because we don't get much out of it, right? I can run 4 or 5 sets of 1/0 a whole lot cheaper than I can run one set of, 750 kc mil or something like that. But there's no magic to it, right? If I have a load that's X amount of amps, I'm just gonna divide it by the number of sets of wire I want to run. That's all there is to it. I just can't be smaller than a 1/0, right? When it comes to parallel conductors, 1/0 is the smallest size. It's kind of the cutoff there. So it has to be the same material, same length, same, characteristics conductor-wise. So all the different parallel runs have to be exactly the same. But we do it basically because of this. So here we go. We got a table in the code book that's based off of one single conductor, right? Well, then how do you deal with, in cases where I got smart and I divided my load by the number of parallel sets that I have, so I'd have a smaller wire to do the same job as one bigger wire would, right? So it makes sense that if I'm dividing my feeders out to make it easier, if I'm using a table that's only based off of one wire, what am I gonna do? I'm gonna add them all back up, right? I'm gonna do the reverse of what I did. So if I had parallel sets of conductors, the math here is simply, I'm going to multiply the number of phases, or the number of sets I have in each phase. It's not the number of wires in one set like we call a set. When I talk about a parallel set, I'm talking about one pipe with an A, B, C in the ground, right? That's a set to me. And that's not what they're talking about in this set, in this code book, or in this sense, they're talking about the set of all of the conductors that are the A-phase conductors. All of the sets that are the B-phase conductors, so on and so forth. So when I've got 5 parallel sets, for example, of 250 kc mil, basically I've got an A-phase in each one of these 5 individual runs, right? And so I'm gonna take 250 kc mil, I'm gonna multiply it times the number of those parallel runs that I have to re-equivalate, is that even a real word?
We'll take it.
To reverse what I did on the parallel side, so it'd be 250 times 5, which is gonna be, right, 1,250,000 circuit mils. And so I'm again gonna take that value and go over here to the table, and where does that fit? Well, it's over 1,100, it'd be what, it'd be 1,250. So I'm gonna be at 3/0, basically. But here's the kicker, it'd be a 3/0 in each one of those individual runs, right? So I'd end up sizing this 3/0.
Still saving money on top of it.
Absolutely,
Right.
absolutely. Okay. All right. What gets weird is that when we talk about the aught sizes, if these were 5 sets of 3/0, for example, or 2/0, for example, instead of 250. So instead of 250 kc mil, now what I've got is 5 sets of 2/0. 2/0 times 5 is 10/0, right?
Sure.
I mean, what's 10/0? Like, it's just the aught's just a label. It's not a mathematical number. It doesn't have any mathematical value to it, right? It's just a label. So to convert or do any math to an aught conductor or any of the AWGs, I've got to convert that to what? To a circular mill value, right? So chapter 9, table 8 is one of the most significant tables in chapter 9, if not the most significant. And one of the uses that we have for it is to convert the AWG or the pot sizes into circular mills. So if you look on page, dang it, I lost it. They really did add a lot of stuff to chapter 9 that didn't need to be in there. Let's go over separate annexes before. It's on page 725. The very third column there has values all the way down until you get to the 250 KC mill. Once you get to 250 KC mill, it goes blank because 250 KC mill is already circular mills, right? It just add 3 zeros to it, so kind of redundantly listed there. But a 2-aught has a value, each one, of 133,100 circular mills. I think, right? All right, so I'm gonna do the same math here, but what I'm gonna do is convert that to 133,100 circular mills and then multiply it times 5, okay? What happens here is I'm gonna get a wire size that's not a real wire size anymore, right? I'm just getting the equivalent of what one wire conductor would be. That's why that table has that weird over 3-aught, whatever, because of these weird wire sizes that we're gonna get when we start multiplying these back together. So 133,100 times 5 gives me 5 something.
665,500.
What was it again, one more time?
665,500.
665,100? 500. There is no such thing as a 665 KC mill, right? But if I go back to the table now, I'm gonna use that to reference where on the table that wire size would be if it didn't exist. And that's, again, I guess my point about why does it not just have the next wire size, but it's because of this reason right here. That's gonna give us a, yeah, because we're over 6, right? So that puts us in the over 600 to 1100. Be a 2-aught times 5, right? So we have 2-aught machines. So I'm using this wire that we artificially created right there to then go back to the table and find out where on the table does that relatively land as a single ungrounded large conductor in service, okay? So when it comes to aught sizes or AUG, I should really not AWG, it's really the aught sizes, because I can't parallel anything smaller than 1-aught. It's gonna be a 1-aught, 2-aught, 3-aught, or 4-aught, where I'd have to go back to page, what was that, page 765? 725? All right, so it probably could be a good idea for you to put a note here underneath this table on page 149. See page 725, did you say? Here. To convert to circular mills. That way, you know, you have to do this on a test and you can get back and forth, okay?
So after you did that step there, you got 665, what was the next step?
Go back to the table, 250.66 on page 149, and see where does that conductor fit on that table. Like where would that single conductor, if I had a single largest ungrounded conductor in my service of 665 KC mill, where would that fit on the table? So I'm just using this as a frame of reference to see where on that prescriptive table that would put me. That would then put me on the second from the bottom, which is over 600 KC mill through 1100 KC mill. It's bigger than 600 KC mill. Remember, 600 KC mill would be 600,000, so I've got 665, 500, right?
Yeah.
So I went past the 600 KC mill quite a bit, but I didn't go past 1100 KC mill, which is technically 1,100,000 circular mills, right?
I guess the standard troubleshooting, you would want to just go to KC mill first. You want to keep it in circular mills.
Personally, I like to keep it in circular mills because that way I don't get confused. But some people prefer it in KC mill, it doesn't really matter. As long as you can remember those 3 zeros after your range.
Wouldn't be an error.
No, this would be fine, because I mean, there's supposed to be a gap between those up at 665 KC mill, what you're saying, yeah, be fine. It's the roundup's not gonna make any difference. If it did, I mean, you'd have to be right there on the edge of one of them, yeah. And if you were right there on the edge, maybe you might wanna go back and just double check, but I think you'd be fine. All right, so, anybody have any questions on that, right? The nice thing about this table is it's always prescriptive. You never have to size your own ground wire. It's already in this table, right? The only time if you do anything different is if they give you a 1/0, 2/0, 3/0, 4/0 in parallel runs, you start have to add them up. That's where that page 725 on the table 8 comes into play, okay? All right, really that's all there is to it. There's not much more complicated notes to say about that. Just remember that 3/0's the biggest size and that's it, okay? Now, let's go to 250.122 and talk about it really quickly. 250.122, like I said, is after I go through an overcurrent device, then it's relative, the ground wire there is relatively sized to that overcurrent device size. But there's no discount for parallel runs. So if I were to have parallel runs coming from a breaker, I'm gonna have a full size based off of this table. There's no discount, there's no undersizing, it's just really simple. So if I had 5 sets of 250 kc mills coming off of a 1,000 amp breaker, for example, right? I'd go to the row that has 1,000 amps on there, and I'm looking at a 2/0, right? I'd have a 2/0 then, a full size that would clear that entire fault current back to that 1,000 amp breaker in each one of those individual runs. So I'd have a 2/0? I'd have 5 2/0s, one in each one of those parallel runs, okay? So from that perspective, it's an easy table, it's easier because there's really not much to it, right? It's based off the breaker size, doesn't matter what the wire size is, really, the wire's really, not even, an issue. And it's always a full size in each one or each parallel run of conductors. At the top up there, 15 amp circuit, what about the 10 amp circuit? Right? Did we just add a 10 amp circuit? Where does that fit? What size do you run for that?
14 copper.
You run 14 copper. Likewise with the 60, so anything larger than 20, there's a 25, a 30, a 35, a 40, 45, 50, 60. All of those would be on the row that's 60, which would be number 10. Yeah, if you go past the row, you're in the next row all the way down. So that's the way to look at this table. The row 1 would be 10 or 15 amps. The second row would be 20. The third row would be 25, 30, 35, 40, 45, 50, and 60 would all be number 10. And the next row would be 70 amp through 100 amp, right? And the row after that would be 110 through 200, so on and so forth. So if you go past a row, you're in the next row all the way down. You wanna know what you guys really suck at? When it comes to this? Y'all really suck at pole lights in parking lots. Yep. How many times have you guys oversized your ungrounded conductors, number 8, number 6, whatever? But you still pull number 12 to ground, don't you?
No, you're crazy.
Yeah,
Right,
yeah. No. So there's a rule here of 250.122. If you look on page, actually I have to go back a page, I guess. 250.122B, it's on the right hand side of page 157. Basically, if you have to oversize or change the size of your ungrounded conductor for any reason, if you're having a problem with, your standard conductors having, distance or resistance being an issue, you're gonna have the same issue with your ground wire as well, right? So what they want you to do is they want you to change it in size to the proportionate relative value that you did to the ungrounded conductor change. It's not the net difference, it's not the number of sizes, it's a proportionate adjustment, right? So if I go up by 50%, for example, on my ungrounded conductors, then I have to add a 50% increase to the grounding conductors. That makes sense?
Your low impedance path back for safety and equipment safety starts to grow, and then you could be potentially a less resistant path, or
Absolutely, absolutely.
because of resistance built.
So it is a proportionate increase though, and I think that's the one thing that people don't get. It's not the net difference, or it's not an add of the same amount, it's a proportionate change. So for example, if I had a number 2 that went to a 2/0 for whatever reason, number 2 to 2/0, right? I'm gonna need circular mills for both of those, by the way, if somebody ever mind grabbing them. If my equipment grounding conductor started out as a number 8, what has to happen here is that the proportionate change from here to here has to be applied to this one as well as a multiplier. So for example, if this doubles times 100% or times 200%, or if this triples or whatever this number is here in relationship proportionately, that has to be multiplied to that number 8.
Alright, so use
like 66,360?
This is 16,510, I think, right? What'd you say this one was, 66,360?
Yep.
And this is 133,200? So I started out with this, right? And then ended up with this, right? Take this number, divide by that number, and tell me what you get on your calculator. So 133,100 divided by 66,360 gives me 2.0057, we'll call it 2.0. You could put a 1 there if you want, but after that, it's not gonna be significantly different enough to make a difference. Alright, so if I were to just double check myself, if I were to take 66,360 times 2.00, whatever that number is, would that give me 133,100? Right? I mean, I'm just trying to check myself to do reverse division and multiplication, right? So if I were to take 66,360 times 2.0, would I get 133,100 or pretty darn close?
Pretty darn close.
Okay. And then rounding off, like I said, the difference.
132,720 is what it is.
That's the proportionate change that those conductors went through, and it has to be applied to the ground wire. Make sense? So I'm just gonna do the same thing down here. This started out at 16,510 times 2.00. 33114. Okay, or circles, right? 33,115 circular mills. Now I'm gonna have to go back to table 8, because I need to know what the next larger standard conductor is. It's got at least that amount of circular mills in it.
R4.
What is it?
R4.
Number 4? What's number 4?
R4 is 41,740.
So number 4 is 41, what'd you say?
740.
And number 3 is?
26240.
Way less, right. So this is the minimum amount of material I'd have to proportionately apply that ground wire, so it'd end up being number 4. You can't do it by steps, because as you get to larger conductors, you know, that proportionate change may be much different, depending on what, you know, we start out and where you ended up. So just take the ending wire size that you ended up with, divide it by the original wire size, and then that multiplier that you get by doing that math, apply it to the ground wire. And then, you know, like I say, go back to the table if you have to actually size the conductor based off of any circular mills, KC mill, AWG or odd size.
Alright, I got lost somewhere.
Okay.
So we're trying to size the ground. That's what we're
Correct.
trying to do?
Equipment ground conductor, EGC.
Or, parallel, okay.
No, not necessarily.
No, just sizing it.
Just size.
It's just where I have a change in the ungrounded conductor, basically my phase conductor. So if I have a change, what I have to do is whatever that proportionate change that happens on the ungrounded conductor has to be applied to the equipment grounded conductor as well, right? And so we're having to do the multiplier. We're trying to figure out where do we end up, or how do we, what's the multiplier that took to go from the first wire size to the end wire size, right? And so there's some easier ways to do this, I get it. There's some, you know, the little cross sectional, you know, you put it on the local, yeah. But for me, this is the easiest way for me to keep it straight, so.
And so you round up, is that what you, because it
Um,
was 33, you had to get with the.
Yeah, this is the minimum amount of material I have to have, and so number 3 doesn't have that amount of circular mills in it, so I have to go.
Number 4 does.
Number 6.
Here's what I'm saying, you round up because that would be higher than the 26,240.
Correct. Yep. I have to have a wire that's got at least the 33,115,
Yeah.
and number 3 is not quite
It's
got enough.
number 6.
Hmm?
Number 6 is the smaller size. Number 3 is going on the size.
What's number 3 got in
52,620. Yeah, because you know you're
it? Why am I saying number 3?
because you're getting them flip flop with the.
I don't know why I'm saying number 3, I shouldn't have been saying number 6, you're right, I was going the wrong way in my mind. And you're absolutely right, sorry, number 6. Number 4 has 41,440, correct?
Right.
Okay. Number 6 is too small, because that's what you're talking about.
Correct, and yeah, that's
Thank
what
you.
number
sorry. That's probably what would make it confused. You know.
Here's the basic way, three, you got.
Thinking
number-
that number three was smaller, number three is bigger.
You got a number four, number two, upgrade, because all of a sudden
Yeah.
600 switches, you gotta upgrade your wire.
I need a wire that's got at least
Upgrade your
Around, you go
ground,
down, you can actually, saying.
Ah, you know what it was?
Down to 26,
All right.
now you go up to 41.
Yeah, you know, I still,
jet lag.
no, it's not even jet lag, it's like, I've never really been comfortable with the fact that our wire sizes get bigger number-wise when they get smaller. Like, right?
Well, it's ways people, the morons out of the trade. We want the money for ourselves.
Well, can anybody tell me why number 10 is classified as number 10, even though it's bigger than number 12, which is a bigger number? There you go, that's right. It's passive,
Yes,
that's right,
yeah,
that's right. It's a shaver. There's less passes on number 10 than there are on number 12, so number 12 takes 12 passes, number 10 takes 10 passes. Just shave it down to that size, so there's less shaving.
Manufacturers.
I know, right?
You have to upsize that.
Doesn't make any
to
sense at all. All right.
52 watt.
So we know how to deal with the conductor if it's based off of a wire size and service, right? We know how to deal with a conductor that's based off of a breaker size. What do you do if you have a separately derived system in the middle of the distribution line, your transformer? Where I don't have a mechanical connection between my secondary and the breaker that's on the primary, and they're not related to each other size-wise anyway, because the ratio, the turn ratio is gonna make that breaker on the primary completely different with the secondary. So what do you do then? You can't make.
Overcurrent protection, go
You
with
can't
the
fix it.
overcurrent protection of the supply to the transformer for the separately derived?
Well, I mean, like, so like, if we're looking at this picture, right, I've got this transformer here. On this side, it makes sense, that branch circuit right there going over there, if it's 20 branch circuit, it'd be this is page, 43. So, I mean, I think, I drew all this out, because I think this makes more sense. You may have, this may make sense to you in your mind anyway, but one thing that always confused me was the XO on the transformer, which has the white wire, the green wire, the bonding wire, I mean, everything terminus is XO. But basically, what we're looking at is I can't base, even though there's a breaker ahead of this conductor technically, right, this bonding jumper over here, even though there's a breaker ahead of it, it's not related in size, and it's not mechanically connected
It's
to
not
it either.
mechanically connected, you're not gonna have a transient short or something go through
Correct.
that one.
So, it doesn't really fit the table 250.122, because that's based on a breaker size. It's not technically a GEC, because we're not dealing with the service. We've actually got a breaker definitely in the distribution system. So we introduced a new table, and that's what this red mark down the bottom, the 250.102C1 is listed as, right? What 250.10C1 does for us is it sizes a conductor in the middle of a distribution where there may be a breaker ahead of it, but not directly related to it like it would be normally. And you use it for sizing a supply side bonding jumper, a system bonding jumper, a main bonding jumper, or a bonding jumper. But it's also our minimum grounded conductor table as well, and it's on page 152. It looks almost identical to the table that we looked at earlier that is based off the service conductor, doesn't it? There's only one difference really between this table and the table on page 149. It's the last row. Yep, when you get into larger parallel sets or larger individual conductors. But beyond that, if you look at anything less than 1100 kc mil, it's exactly the same table. It doesn't act any different, right? But what happened was we used to use one table for both. Remember, the other table stops at a 3-dot, right?
Right.
What if you have a 1600 amp transformer that's got a secondary that's got way more than 200 amps of current on that neutral conductor? I mean, it happens all the time, right? I mean, you could have 400 or 500 amps on that grounded conductor on that secondary side of that transformer.
600.
So if I'm using a table that limits me to a 3-dot, that's pretty screwed up. If I'm using the same table for both the grounded conductor, all the bonding jumpers, and for my GEC. So we took the same table, and we changed the last row.
So,
But it's a significant change. Yeah,
so this is specifically designed for separately derived systems. Within the current system, you've already
correct,
made your sizes for EGC and all that.
correct, yep. It's also considered now the minimum neutral conductor. If you're doing any kind of derating of a neutral, you're gonna have two places to look. This is a table of the minimum conductor based off of the wire size in service, excuse me, in the circuit, I guess I should say. Or your calculated value for your neutral demand.
Are generators and inverters considered separately derived systems, or do they, supplies
If they're mechanically disconnected on the grounded conductor, yes.
through a transformer?
Through the transformer, they're separately derived.
So an inverter for solar system would be a separately
Absolutely.
derived system,
Absolutely.
if it is an inverter.
Absolutely, yeah.
Okay.
Alright, so, here's the difference, right? Everything we talked about on the table before was always prescriptive. Doesn't matter what size that was that we ended up with, we went back to the table and we had either something less than a $3, we had $3, right, as a wire size. I didn't have to size my own ground wire, it was always referred back to the table because the table would give me the size of the ground. Here's the problem, this bottom row basically says, look, if you go over 1100 kC mil, you have to now size your own ground wire. We're no longer gonna have it prescriptive on the table. So it just gave us a little bit more breathing room for secondaries that had larger demand loads on the grounded conductor, so we could now size them a little bit more appropriately. So here's what we do. We're gonna take the sum of the equivalent, see, that's not bad. Parallel. There's two R's and two L's. Conductors in the sets, right? And we're talking about the A, the B, or the C, right? We're not talking about the, or with the number of A's, the number of B's, the number of C's, right? And then we're gonna multiply that times 0.125. Not 1.25, 0.125, okay? And that's gonna give us the minimum size for the ground wire where we don't have one. So for example, let's say that we had 6 parallel sheets, or 6 parallel sets. 1, 2, 3, 4, 5, 6. We'll call them all a 250 kC mil. Right? So I have an A, a B, a C that are all 250 kC mil, and I've got 6 parallel runs of that 250 kC mil, all each one of those pipes identical, right? So to size this, just like we did the other table, if I have 6 sets, I would take that A phase at 250 and multiply it times 6, right? 250 kC mil times 6, because I've got 1, 2, 3, 4, 5, 6 identical runs, right? So that would give me 1,500. And here is where I will almost suggest that you leave it in circular mills and not do it in kC mil. But if you're not careful, it'll be real easy to get confused here. 1,500 kC mil is
1.5 million.
1.5 million, right? I'm gonna multiply that combined number times 0.125. And it's not, and like I said, I want you to put it down underneath that table just like that so that you don't accidentally do the 1.25. That's a very common mistake to make, but 12.5% versus 125% are two different numbers. It's 12.5% times 0.125.
187,500.
Yeah, 187,500. So what I got here, after I did that times 0.125, that is the minimum amount of circular mills that I have to have in that.
Each conduit.
That's right.
Each conduit,
That's right.
which would be number 6.
I'm gonna have to go back and see where that fits.
Yeah, it's over number 8.
Yeah, at the bottom, just put times 0.125, just so that you don't accidentally.
Under 250, 102.
Yep. You just said it exactly what I, times 0.125, yeah. Your habit's gonna be 1.125, because we use that all the time for community studio, right? So that's gonna be what I'm trying to prevent you
basically, it shows, 4-aught would be the,
What's 3-aught?
closest, 167, 800,
Yeah, so 3-aught would've been just a little shy, so 4-aught's got 233,
211.
211. 11 what? 600?
Yes, sir.
Yeah, there it is.
So I ended up having to go to a 4-aught there because that's not, that's more than what a 3-aught has, certainly.
So that would be for each ground.
That's 6 of them, I'd have a 4-aught in each one of these runs. And that's how it works. The difference between this table and the other table is that I'm sizing my own ground wire in this case, right? That's a significant difference, right? The other table, it didn't matter what size it was. If I had done this math as a GEC, I'd have a 3-aught in each one of them, correct? Because the 3-aught is the biggest wire required to have for another table. But as a separately drive system, if I'm doing a bonding jumper or grounding conductor, then I'm gonna end up with a 4-aught, which is a little bit bigger conductor, and that makes sense. That's kind of why we did it this way, so that we'd be able to have a larger conductor than a 3-aught when you have larger, loads on that, secondary side. Okay.
And this,
So-
and we only do this calculation for what, I mean, sizing our own ground, but that was for the, you said. you
If
brought that-
anything, any question that has the word jumper in it, or anything that's a grounded conductor in parallel runs, that's gonna be the two identifiers, I think. So on the secondary side, where you have a transformer, basically is what's causing this one. Okay?
So jumper or grounded, or
A grounded conductor.
under, a
Neutral.
grounded conductor.
Yep.
It says it right there in the,
First word on the table, grounded conductor.
right on the, top of it.
And everything else has the word jumper behind it, so that's, yeah, there you go. Yeah. SSBJ or SBJ or a, I just, SBJ or SSBJ, just, why would you say
When
that?
you throw a new transformer line, you get your 277 480 panel, cause you're now doing 3-phase stuff in place, then you can size a secondary side.
Yep.
So, see right here.
You'll notice too, we're talking about, if you look at that, what I've got, the way I've got it drawn, your supply side bonding jumper and your system bonding jumper, which is down the bottom, both of those terminate to the same XO, right? So does your grounding conductor on the secondary side. So all three of those conductors, which are all three specifically listed under that table, they're all sized the same, right? Use the same table, same method. So the only note I would probably also tell you is to put a note to see page 725, because you are gonna end up having to go back to table 8 as a last step if you're in that bottom row, because you're gonna have to manually size your.
725 for conversion.
Yep, so you put times 0.11 or 125 down on the bottom, and just a note to yourself, see page 725, size your grounded conductor in table 8. Okay? All right, the other thing that needs to be pointed out in dot 66, we need to go back just a little bit further than dot 66, and we're talking about the grounding electroconductor system, the earthing system. It starts in part 3 on page 145 under 250.50, the grounding electrode system, and under dot 52, it gives us a list of 7 specific things that are allowed to be permitted to be considered grounding electrodes, and those are your Uber, your let's see, your underground water pipe, your metal in-ground support structure, building steel is building steel is under number 2. Your concrete or your Uber is on page 146 under number 3. Ground ring is listed under number 4. Rod and pipe electrodes are listed under number 5. Other listed electrodes are number 6, and then finally plate electrodes, which are number 7. I can't imagine another local metal underground system or structure other than gas, which gas is not permitted to be considered a grounding electrode. So even though you have to bond it, it's not considered part of your GECs, right? What other kind of local metal underground system or structure would you have that didn't get any of those other ones? That's under number 1, that's the first one they list there.
What page are we?
I'm on page 145, 146, 250.52A, 1, 2, 3, 4, 5, 6. I mean, if it's part of building still, then it would be under number, 2. If it was UFR, it'd be number 3. So what other, I don't know what, other listed, I'm sorry, other local metal underground system or structure.
Could it be like a?
My bunker?
Like,
I mean, I got some,
like septic or something?
what are those shipping containers? Connex buried in my backyard.
Yeah.
I use that, that up to my GC.
Antennas, sewer.
Sewer, but only if it's metal. And then you're talking about a in-ground water pipe, I mean, technically, right?
Or what about, like septic or something, you would maybe have,
Again, it'd have to be metal, and in there, if it's metal and it's conduit or pipe wise, I'd expect to see like a 10-foot rule.
Lightning
blah, blah, blah.
protection?
Huh?
Lightning protection?
That's a ground ring.
I think that would be, well, that's part of the ground
ring
system,
Yeah.
where you would make.
I don't know, anyway, just curious, I always wondered what they were talking about there, it seemed kinda ominous to me, but but in ground, not a float in, right, so.
We're leaving it open for the space invaders.
It's that
so-
one thing that doesn't.
Okay. What's really important about this is that, that's basically what's allowed to be considered a ground electrode. Dot 53, which is on the right-hand column, page 146, how you put them all together, right? I urge you to start on page 145 under part 3 and read every single item in part 3 because you'll see it on a test some way or another. It's either gonna be what is or what compromises a ground electrode conductor, or how do you put them together, what's the minimum size, so on and so forth. Especially for example on the dot 53A4, the rod and pipe electrodes, there's a lot of rules that they have to be not exceeding 45 degrees of an angle, and you can't do that, you gotta lay them flat at 30 inches deep. You gotta have at least 8 foot in contact, right? Is it 8 foot or 10 feet? 8 foot. If you can't drive it perpendicular, right? You start out with an 8-foot ground rod, right?
you can lay it in.
Don't cut the top off, and then, because I mean, it's too obvious, right?
You gotta leave the numbers at the top.
That's right,
Cut the
yeah.
other side off.
Oh my God. Let's make it look like you tried.
I think you can lay it in the ground. You can also do it at an angle.
How many ground rods do I have to have in service?
I've done it.
Two?
Two.
You're all fired.
What?
Why do I have to have 2 ground rods? Show me the code book where it says I have to have 2 ground rods.
I thought that was jurisdictional.
What? Okay. So the rule, I don't understand what's hard for inspectors to understand this, but basically,
I think that's for.
250.53A, right, rod and pipe play electrodes. Number 2, supplemental electrode required. A single rod, pipe, or plate electrode shall be supplemented by an additional electrode of a type specified in A2 through A8. Now, if I remember correctly, A2 through A8 we just talked about, right? Those are your building steel, concrete, hewers, so on and so forth. So if I have one of those specified, then I don't have to have another ground rod.
Right, you don't have,
If I have a single ground rod and I have another grounding conductor,
Or-
I don't have to have,
Or unless your ohm rating is under 25 ohms. For
yeah,
the
a single
resistance
pipe or
ground
less,
check.
it shall not be required.
Then you go over 6 foot, pop another one.
No, I don't even have to have ground rod at all.
As long as you have those other.
If I have a ground resistance 25 ohms or less, the additional supplemental electrode is not even required.
Right.
So I don't.
Well, that's what I'm saying, if it's above that, then you would need another one, to say polygon.
Well, but then I'm only required to have one. It would be the supplemental ground rod, so that would be my supplemental ground. There's nowhere in the code book that requires to have 2 ground rods. It's stupid.
No, that's jurisdictional, yeah, that's a jurisdictional thing.
Because of our.
You know, you're right, if it's more than 25 homes after that,
Well,
they
it is,
still have to have.
it is in California, started that, it's spread.
I do ground soil resistance in Dallas is like 3.9 ohms or something, it's just really low, it's not even near 25. I did a bunch of those 5G wireless burst transmitters back in years ago, but I just like.
High desert sand is where you run into that.
Or any soil that doesn't have much moisture content.
Period.
But, I argued with every single Dallas inspector that he was not gonna drive 2 ground rods in existing, because we were putting these on top of the utility poles that were already cast in concrete with sidewalks and stuff like that. You want me to drill 2 holes, and what am I gonna do with the wire to connect them? Right? I mean, I gotta tie them together. And we're talking about like crosswalks and streets and
Yeah.
sidewalks. I mean, what am I gonna do with the wire? You know, I mean, run all the way back to the building that's not even connected to what I'm doing, and then run it across
Double the
there.
wire, double the material, double the
So,
labor.
yeah, I ended up buying a Megger, and I took a picture of every single soil resistant.
That generally, like, notice, it's well worth the money spent on that.
Absolutely, because otherwise, I mean, they'd kill us.
Yeah.
Anyway, just thought I would point that out. Okay, maximum size conductor that has to be connected to a ground rod is a number 6, and that is under, number E here, so it's 250.53E. Page 147, left-hand column, just FYI. The earth shall not be used as an effective ground fault current path, and that's under 250.54. What else is worth pointing out? I think that's probably the biggest parts. Bonding jumpers electrode spacing, 6 feet of separation from any other ground electrode conductor, so, that's what I think he mentioned just a minute ago as well. That's under, B, 250.53B electrode spacing. More than one of the electrodes, the type specified in 8.5 through 7 each shall be not less than 6 feet from any other electrode of any other grounding system. And you can't use rebar as a conductor to interconnect electrode to ground electrode system. Now, you can use it as a ground electrode conductor if it's what, bigger than ½ inches of what it is. ½ inch, isn't it? It's got at least 10 feet. Is it 20 feet? It is 20 feet.
Where's that at?
Top page 146 under 3, concrete case electrode number 1. It's 20 feet of either, ½ inch minimum, 20 feet in length for if immobile pieces, held together by steel tie wires, exothermic welding. Which, that one I've never agreed with, because steel tie wires are nowhere near the equivalent of an exothermic welding, connection, but anyway. Or bare copper, not smaller than 4. All right, not exposed to physical damage. If you look on page 147 under 250.64B, securely fastened to the surface in which it's carried. That's an exposed PVC conductor where it may be exposed against physical damage. If it's not exposed to physical damage, number 6 or larger, not exposed to physical damage shall be permitted to run along the surface without metal cover or protection. But if it is exposed to physical damage, number 6 or larger shall be protected by one of the following types, and that's on page 147, right-hand column under 250.64B 1 and 2. And then the aluminum, when did I pass the aluminum? Under 250.64A2, 18 inches of the bottom of the enclosure, 18 inches of the earth under A3. Aluminum, termination of aluminum can't be terminated within 18 inches of the earth. Okay. All right, I think that's worth all this worth discussing there. And just make sure that you have on your must-read section, page 145, starting part 3, 250.50, all the way through and including, part 5, the bonding, which is on page 150 and 151. So I would read 250.50 through and including 250.96.
Just say, safe to say all of Article 250.
Well, yeah, I mean, yes, but, I mean, there's a lot of stuff in 250 that is really kind of hard to understand and pretty rare, but, 250.118 is also a section that I really, encourage you to read through. 250.118 is where I've got equipment grounding conductors that aren't an actual wire, so things that could be used in lieu of a wire as an EGC are listed under 250.118, and, pay careful attention to flexible conduit. Flexible conduit is permitted as an EGC where it meets certain size requirements, and it has an equivalent capacity, to go with it. So for example, listed liquid type flexible metal conduit on page 156 under 250.118A6. If it's a trade size, 3/8 to a 1/2 inch, you can use it. It's rated at 20 amps or less. If it's larger, 3/4 through 1 1/4, it's related to a 60 amp EGC. But it can't exceed 6 feet, and it can't be where you're using it for any kind of flexible purposes. So for example, if you're using it for a transformer connection or something of that nature, then that doesn't fly. Okay? All right, I think that is most of what I wanted to talk to you about there, and let's move on. All right, let's do a couple of these real quick just to see how you do. Again, lightning strike being the focus of what that GEC system is. We want to make sure we have an effective ground fault pathway so that we don't feed back into our distribution system. And so that's kind of what the GEC's purpose is. If I had 250 KC mil aluminum copper feeder, what would be the minimum size GEC necessary for that service? A 250 KC mil copper feeder using 250.66, what would be the minimum size GEC required for that service? So I'm gonna go to 250.66. I'm sizing for the service. 250 KC mil copper. That would put me on this 4th row, right, over 3 up through 350. And be a number 2 copper. Anybody not see that?
250, yeah. Number 2 copy.
Yeah, like I said, be careful of that over 3 ups a bit. I mean, you just make sure you're in the right row. What if it was an aluminum feeder?
Number 250?
Aluminum 250 KC mil would have what size GEC?
Number
2. Number 2.
Still haven't heard right answer.
Copper?
What about number 4? If I had aluminum, if I had to take a KC mil, 250 KC mil aluminum feeder, right? That puts me in the 2nd column, puts me on the 3rd row. Why am I answering number 4 instead of number 2? Y'all are answering, you're telling me number 2 because I'm giving you aluminum feeder, but I'm not
Oh, because
answering.
you said 250, so 4 or 250.
You're saying number 4, because we should never, otherwise said so.
Yeah, my answer is always gonna be copper, period, unless they specifically say they want the answer in aluminum. Right. It's just minor details like that, but, a 250 KC mil aluminum feeder, in the way they've got that written there, my answer would be a number 4 copper. Right? Yeah, 4 copper. Alright, neutrals, bonding jumpers, that's 250.102C1. And then equipment grounding conductors, the 250.122. If I had a 70 amp fuse, what would be my minimum size equipment grounding conductor?
250 amp? Oh, 70 amp?
70 amp.
Number 8?
So I'm gonna go to 250.122. I've already passed the 60, yep, so anything from 70 to 100 would be number 8.
Number 8 copper.
Number 8 copper.
6.
Yeah. Or number 6 aluminum, if they have to. 250 KC aluminum feeder fed with a 250 amp breaker will be with no size ground necessary. Which table am I using for this?
EGC? Just 66.
250.1, 222 or .CP6?
122. Oh, feeder, 66.
No, make up your mind, after I was saying,
It says feeder.
which comes first, the chicken or the egg?
Oh,
Which
that's
comes first, chicken or egg?
But
If there's a breaker ahead of it, it
But
is
it's-
not .66, right?
Yeah, but it's a
just
breaker.
not. I mean, if there's a breaker ahead of it, we're not in .66.
Yeah.
So it doesn't matter if it's a feeder or branch circuit, really, at that point, we're talking about the overcurrent device being ahead of it, that's gonna be .122.
Okay.
So the EG,
The sub feeder.
EG sees everything has the breaker, right?
Yep, if there's a breaker ahead of it, it has to be .122.
Yeah, it's like on the other side.
Excusable disconnect, yeah.
So this is 250 would round up?
So the wire, in this case, the wire size got nothing to do with it, right? It's this breaker, right? The breaker is ahead of that feeder, so it's a 250 fed from a 250 KC mill breaker, so the breaker is really, so 250 KC mill, excuse me, 250 amp would be number 4. I've seen them give you the wire size, asking for an equipment grounding conductor wire size or ground wire, right? And so just don't let the wire size, if it's not important, don't let it bother you, right? If there's a breaker listed in question and that wire's coming after that breaker, then you're in top one.
So would they ever do it the opposite way, ask you what size is ahead of? the
Yeah,
breaker?
if that feeder would have been ahead of that breaker, then I would argue, yeah, .66 would be where we would be at.
So if they worded that, like given a 250 KC mill aluminum feeder, that's
Fed.
feeding a 250 amp breaker,
Fed
calculated minimum
from,
gravity.
not feeding to, but fed from. That's the word, yeah.
I'm saying, but if they change the wording. to
Oh, yes,
fed
yes.
to a
Yes,
250 amp
yes, then
breaker.
it would
Say it again,
be
say it
one-
again, please.
Then it would be 66, yeah.
Yeah.
Okay.
Say that again one more time, please.
So his question, the question asks from the 250 amp breaker, but if they change the wording to an aluminum 250 KC mill aluminum feeder fed
Feeding
to
to-
a 250 amp breaker, calculate the
Then you'd be on the
minimum
front
gravity.
side.
Then we'd be at 66.
Yeah,
Yeah.
and they'll do that to confuse us a lot, right?
Oh,
Good
yeah.
clarification.
That just happened right now.
Two breaker.
All right.
To and fro.
2 parallel sets of 4-aught, what's the minimum size supply side bonding jumper necessary? 4-aught. So that's at 250.102 C1. 2 parallel sets of 4-aught.
That's why I was.
They like to, so they use the word parallel run in a way, sets. They use the word sets in a different way than what we use the word sets. To me, a set is a run of wire in a pipe, right? To them, a set is a set of phase conductors that have been paralleled into multiple different.
One or two copper.
Remember, parallel sets, the first thing we have to do is add them back together, right? Because the table that I'm dealing with here is only gonna be based off of one single largest ungrounded conductor in the service. So I'm gonna have to take 4-aught times 2 and,
So then you gotta go do the KC mills and add it all up. And
what is it,
it's-
211,600, right? Is that what number what it is?
Yeah.
Times 2, so it's 423.
422.
Now, that's not a
Don't tell
real.
you have to go to,
Say-
break it, don't tell you how to break it down in case of meals.
You do.
If you, cause it's 2 sets, right?
That's right.
So it'd be a number 3 odd.
Number. Do we have to multiply like 0.125?
No,
No.
3.
as long as I don't go past 1100 KC mil, right? Anything under KC mil, at 1100, I'm using the table still, right? So what happened was this 423 KC mil that I got, when I took 2 sets of 4-aught, which is 211,600 times 2, right? That gave me 423
Four twenty-three, 200.
200, okay, so 423.2 KC mill, right?
And back on 725, he's
That
3 off.
is what I'm gonna go back to the table and find where does that wire fit on the table.
back to seven,
Yep.
No, in this case, you're gonna go back to the table on page 140. Yeah.
102 and 66 are almost identical.
They are, except that last two, after you go,
Yeah.
the only time it changes is if you go over 1100 KC.
Yeah. So on that table 102, what can we put as far as the initials, like what we did for 66, we put the GEC? So, I mean, you know.
Like I said, it's either a grounding conductor or a jumper. If you see either one of those, that's kind of gonna be your best clue, I think.
Okay,
Lots of parallel sets, and it's usually, I mean, I think the 4-aught stuff is where people get confused, cause you gotta go to table 8 to get the conversion, right? Do the math and then go back to the other table, except where you go over 1100 KC mill, because then you're no longer going back to the table, you're doing the 112% in size of your own, and you're gonna end up on table 8, size of your own wire based off of that. I can't make this shit up, I mean, I just. What was the question? We come back here to over.
Over 3 off.
Yeah, no, I'd be over 350, or 600. I did it with the 1-off.
Yeah.
Good with that? That 423 KC mill is bigger than 350 KC mill, right? I'm gonna go back and so technically we're on the table on page 152, right? That 423 KC mill is bigger than a 350, but it's not bigger than 600, so that puts us into the third from the bottom row, which is the 1-aught copper. And I'd have one 1-aught on each parallel set. By the way, in no case am I ever gonna be required to have a larger, GEC or grounding conductor than the face right here. So if your math ever got to the point where you have parallel sets, so for example, I had like 10 parallel sets of 1-aught, at some point, my wire size would be bigger than the 1-aught based off the math, when you just go add them back together. So you're allowed to run the same size. Correct, that's right. You're not required to be larger than the grounding conductor. Alright, 3 parallel sets of 300 KC mill would be the minimum size of the size. In this case, if it's not an aught size, then, it's really nice, I mean, you're just gonna add those times 3, right?
Once you get over that, it's 3-aught.
So that puts me at a 900 KC mill equivalent for one conductor, cause I've got 3 parallel runs, so I'm gonna take the 300 KC mill times 3 runs, it gives me a 900 KC mill. And that is still prescriptive wire size, cause it doesn't go past the 1100, so I'm over 6 to 1100, be a 2-aught. And I'd have 3 2-aughts, one in each parallel run. Good. And finally, the 4 parallel sets of 600 would be what? There you go. This is where the one main significant difference happens, is where I go over 1100 KC mills. So when I take this 4 times 6 and get 2,400,000, that's where I've got to use the 112%, right? So I'm gonna take that 2,400,000 certain mills times 0.112.
So here,
And now I'm the size of my own ground wire now, right? Cause I'm no longer on the table, so I'm gonna have to go back to table 8.
0.125?
Yeah. 0.112, yeah, 0.125.
Okay. I was like, damn it.
That's the only number. So 2,400,000 times 0.125 gives you, I think 300,000.
Yeah, it's 300,000.
Which is
Yeah,
standard
that
size.
gets down to, number two copper.
Say it again? Yeah, because you're over the.
For each copy.
Correct. Yeah. And only when I'm dealing with this table right here, right? Is that other table up, would just max out the three options, that's not right, but as a, bonding network, that makes it a, 300 KC mill. And, that makes sense, because your parallel sets are 600, so you're not above the underground conductor, so you're at, you'd have 4 300 KC mill conductors, 1 each on the parallel sets. All right, we talked about some definitions, talked about multifamily. There's a couple other things too, where definitions kind of, mess with you, I think, somewhat. An example here would be the dryers on 220.54. We talked about ranges briefly earlier, but let's talk about the table 220.54, real quickly, and that is on page 96. 220.54, up underneath 220.54. The dryer table is kind of a weird table. It's not really that hard or complicated, but they go past 11 dryers, they get kind of funky with some math there. And then you go past 23, and then there's some more funky math. There's only one calculation though, it just depends on the number of dryers you have, so you don't have to work your way through the table. It's literally whatever the number you have, find where you're at, and then do the math in that row. So look at it like this, 11 dryers was 47%?
Yes.
Right. These are multiplying factors, just like we had with the range table. So if I had 11 dryers, the word dryer, it means how many watts? And where did you get that?
So minimum size.
The table, by the way, is on the top right-hand side of page 96, right there. Okay. So 220.54 specifically, the article says, if I'm gonna use that table, I cannot use a dryer value rated less than 5,000. So I want you to write that at the top of the table on the page there. Minimum 5,000 watts, that way you don't actually try to use the table. There's several questions that give you dryers that are rated at 4,500 watts. That's not gonna cut it. I'm gonna end up having to bump those up to at least 5,000 the minimum before I do the application of the table. Okay. So 11 dryers, they just gave me the word dryer. I'm just gonna safely assume that each one of those dryers is equal to 5,000 watts because that's the minimum rating, okay? The 47% is gonna be multiplied against the nameplate or the connected load. So I would take 11 dryers times 5,000 watts. Which would give me, what is that?
55,000.
Thank you very much, sir.
Times 0.47,
Times 0.47.
25,850.
And what if I wanted to know what the minimum grounding conductor was?
Well, times 240 to get an amperage rating out of it.
Is this not, this is VA, isn't it? Yeah, it's in VA, sorry.
Yeah, just one.
VA.
Old dams.
What about if I'm just asking for the demand on the grounding conductor in VA? What's the first example I gave you all this morning?
That was so long ago.
It was a range, right? Rated for 14,000, does that ring any bells? We were looking for the grounding conductor, and so we went through all that bull, stuff, and we ended up with 70%.
Yes.
So on dryers or ranges, they could ask you for the grounding conductor, and that's an additional 70%. So if this would be the unground conductors, they wanted the range conductor to just take 70% of that
You said
number.
grounding conductor again.
So my phase conductor would be based off of 25,850 VA.
But your grounding conductor would be based off of that 0.70.
That's right, 70%.
That's why that 0.70.
Or 30% less for the 70%. Okay, that applies to the dryers or ranges. You might want to put a note maybe at the bottom of the table, grounding conductor at 70%, that way you don't forget that little note. And that came from 220.61B.
Grounding conductor, you would add it to the.
On the dryer table here. ground conductor at, or neutral conductor, or whatever makes more sense to you, at 70%, just as a note, okay? I took 11 dryers, each one of them rated at a minimum of 5,000 watts, so 11 times 5,000. So that'd be my total connected load, all of the dryers at 100%. And then the derating of the table would be the 47%. Now, they got really lazy because the 12th dryer would have been 46%. The 13th dryer would have been 45%. 12th dryer would have been 44%, and so forth. So every dryer that I added, they just took 1% off of where I just got left off, right? So it would have been a really long table. So what they did was they got cute. They said anything more than 11, just take 1% minus every dryer past 11, right? So if I had 22 dryers, all I'm gonna do is go, okay, well, that's more than the 11. It's not more than the 23, so that puts me in that little section there where it says 1% minus from this number here for each dryer that goes past that number where I left off that 47 at, right?
And that was on both of my tests.
So there's 11 dryers, right? Beyond what this was. Each one of these is times 1%. So I'm gonna take 11% of 47. So I need 36% for 22 dryers.
Yep.
I'm gonna do that, I'm gonna do that again.
Quick question, so what happens if you get past that, 47%?
Then you're at a 0.5%, but you're coming off of 35%, which is where so example, 23 dryers is 35%, right? Is that what it says?
24.
Well, the 23 ended up at 47 minus 1%. So, well, what if I had 23 dryers? Let's just do that. If I had 23 dryers. So I had 23 dryers, right? Now, the table stops at 11, which was 47%. Everybody with me? So how many past 11 do I go? 12. Each one of those 12 is gonna cost me 1%.
So that's 47 minus another 12%.
So 47 minus 12% gives me 35.
Then you take the total.
Well, if it's 11, yep. Each one of those 12, that's right, from the 47. So you see, we tiered our steps, right? So the 0.5% already has the first part built into it, so you don't have to worry about it.
So it's 5,000 watts times 23 dryers times 0.35%.
There you go. If I had 24 dryers, then I'm now no longer worried about this. Because,
I got 40,000 watts, 47.
right? So this 35% already has that first business built into it, that's right. So if I'd have had 24 dryers, then I'm past 23, where we ended up at 35 originally. The only difference is now it's a 0.5% instead of 4%.
So that'd have been 35.5%.
Then 34.5.
34.5.
Yep. Right. So you don't have to do both, you just pick your poison, whichever you're, and then after you go past 43, it's simply 25%. So I'm gonna give you a doozy. Give me the total demand in volt amps for the grounded conductor for 41 dryers.
Whoa.
41 dryers. I'm looking for the demand on the grounded conductor. NVA. NVA. So I got 41 dryers. Assume 5,000 if I don't tell you, another specific number. So it's a nameplate or 5,000, whichever is larger, right? So if they gave me 4,500, I would bump it up to 5,000. If they gave me 5,500, I would go to 5,500. So 41 dryers. I'm gonna take 41 from, what do I subtract from 41? 30. 30, what?
What are you doing?
Oh, 35 minus.
You It just said 43 or 44.
Forty-one minus twenty-three.
There you go, 41 minus 23. The first 23 is where I get that 35%, right? So it's gonna be 35% as a starting point. Anything past this, I'm taking 0.5% off of that, so I'm just 41 minus the 23 is what I'm looking for, which is what? 18? So if I have 18, each one of those is at, that gives me what, 9? So 35% minus 9% is 18 times 0.5 would be 9, right? Which gives me what, 24 or 26? It's 24, right? Now what do I do? 70% of what? Now how do I apply to what? What do I do with this 24%? Now that I've got this, I've gone all the trouble to get that, what do I do with it?
Yeah, you gotta times up your dryers, so you
Okay.
got 205,000 watts.
Okay, excellent. So 41 dryers, each at 5,000 minimum watts, right?
Yep.
So that gives me 200 and what, 5,000?
Times 0.24,
The 205?
that's 49,200 watts.
Times 5,000. Yeah, 205. So 205,000 my connected load, that's for all of them combined, right? That's what this 24% does for me, is it derates that 205,000 for the ungrounded conductors. I'm gonna take this 24% against that connected load of 205,000.
40 watts.
And that would give me the demand on the ungrounded conductors, the base conductors,
43 amps.
49,200, right? So 49,200 VA, which is what I would size the ungrounded base conductors based off of that number right there, divided by 240, whatever the capacity would be.
Times 0.70 would give you 34,440.
There you go. That's the
Divided by
last decimal.
240, then that gives you that 143.5 amps.
49,200 times 0.7. I actually support VA, so you don't have to do that the very last step.
Was that times 70%?
Times
Yeah,
70%.
times 70%.
34,440. 34,440. VA. And I asked for it in VA, so that would be good enough. Is it 26%?
Yeah, once you get it,
Yeah.
you'll never lose it up.
No, I'm not over 43, I'm at 41. Where's 43 coming from?
Can't rush through it, because if it starts skipping it, as well.
Yeah, if I go past 40, if I go to 43 or lower, then it's just 25%. But that's the step.
One driver than 43.
It's not hard, you just gotta.
Well, you gotta slow, for me, I gotta slow down when I'm like placing it, there's 11 of them, and then the overflow, that's just, that's what you're
Right here, so I'm getting lost.
Oh, I see what you're saying, when I asked that earlier. Right? You little guy. I see what you're saying. Well, the 41 dryer gives us 24%, which is less than 24%, is what you're saying.
Well, the math, 35 bucks, I guess,
26. So I asked you guys before I did that. I was thinking that too.
Theoretically.
That's what I get for listening to you guys. 26%, which is gonna change this and this. What's 205,000 times 26?
53.
Thank you. 3?
53,300.
Okay, and then 70% of that would be,
37,310.
There's that.
and you're right, because that makes perfect sense, if there's been 24, that's less than 25% each for Alright. I said was it 26% or 24%, I should have done my own math, so. I think my own fault. Alright, I guess that means let's take a break. Give you 10 minutes. Watts and VA, by the way, are the same thing for y'all on this test, there's no difference. Now, yeah, it's 100% unity. Now, in convention, the watts is the connected load and the VA is the command load, right? So on your plans, you'll see that they'll list the equipment nameplates in watts, but after they've taken whatever, diversity factors or derating factors, they'll list it in VA, and so, but on the test, it's the same value. Is the nameplate or the connected load. And so after you have applied any manufacturers, derating factors, things of that nature, that then becomes a recommended VA. There's technically, there's true power versus apparent power, which is, where you supply a certain power factor, where your VA and loads are not gonna be the same thing at all, but on the test, they consider them to be 100% or. And in fact, in your code book, specifically these two tables, if you look at 250.54, the last sentence there, as well as 250.55, both of those tell you that the tables are considered to be equivalent. KVA is considered the same thing as KW for loads calculated in the section, so.
So if you would have asked,
Lost me on the 35% to 9%.
Okay. How did it get from this? Where did this come from?
Yeah,
So if I had 41 dryers, right?
right.
It's anything bigger than 23 is a 0.5% subtracted from 35%. So what I did was I took 41 dryers minus 23 dryers, gives me 18 dryers past that cutoff.
Right,
Each one of those is a 0.5%, so 0.5% of 18 is 9%.
okay.
And then the 35 is given there as the starting point, minus the 9%, which is where I made a mistake. I wrote 24%, but it's actually 35 minus 9 would be 26%. So this is a derating factor, right? So we went to all that trouble just to get this number here, but that's not the end of it. We still have to go back up to the number of dryers, the nameplate rating,
Yeah.
total connected load, demand factor, demand load, and then grounding conductor, and the final step if they ask you for that, which is the final step.
I wouldn't have corrected you, but if you're over 43,
No, I'm glad you did, because it makes perfect sense.
You would stay at 25.
Right.
If you're 45, 46, 47 dryers, you're all 25.
Yeah, no, I'm glad you did that.
So the 9% was from 18 dryers.
Right, at a 0.5% each.
Do you get the, before you get to the.
Dryers, that's, I feel like it's easy. I remember last time, I don't know if there's ever one day two where the calculation starts.
So yeah, this 35%
There's a multi-step.
listed there, already has that step taken into it.
And I thought it was the multi-family stuff.
That's a common question, because you wanna try to go through the hierarchy, but that 35% already has the 47 minus 1% for each one of those above.
When I was going through that, I did see that.
The 1%? Yeah.
Yeah, that's.
Yep, so we had 47 and 11, right? And then each one of those past that takes you all the way back to 35%. The 23rd dryer would have been 35%.
So then, at that point, that's when I think 0.5% over all the way down.
Yeah, 'cause it's not like I'm throwing it in.
Well, because if you went down to 43, which I said, that's.
Yeah, so it's 47 to 35 and 25 is the three platform.
Basically, all they're doing is break it down for you, so you don't have to do quite as much.
It would have been a really long table to write it out, long columns, and so all they did was just take I mean, basically, anything with 11, that's right, yeah. Cause the 12th dryer all the way through 23 would have been 1% for each dryer, so they just collapsed it into the math, right? And then after that, it was anything past 23 was a 0.5%. For a while, I made tables vehicles that had all of those steps on there, but I think that was just as confusing as learning the math, so I just gave up and started going back to the basics.
Well, I mean, I might be able to do all of that, it would be rough. If I feel like I'm not preparing well enough.
Found one there,
Yeah, well, many things with the house is, the mom is technically in charge of her stuff. Has no idea what she's doing. She obviously can dissect what's going on with the finances.
You're just going straight down.
All that stuff.
Yeah, well, and maybe like the last one was the Allen test too.
You got 41 dryers, total,
They're doing
right?
things with their.
Yeah, that's
Track,
check.
23.
So I don't know what it's.
Were the last ones all motor questions?
Well, which is.
I mean, the last test I
Sit
took
down
before that.
it's at 18. So yeah, it's at 20, subtract 23.
It's hard for you to believe you make a zero on
So you
that.
got 18. Divide that 18.
I wonder if somebody will just kick the end on you guys.
Put it in.
That gives you your 9%. So,
Cause they, depending on how they stack them, I mean, I can see that being towards the end of the test, like the last 20.
basically,
Yeah.
if you were to do the math, all the way down, 23, so basically, it's just one right around.
No, that's pretty good.
Yeah.
So that's not.
Divided by makes sense.
No, it starts at 27%.
Not yet. I'm gonna get the new one here.
And it
before
works
I
its
leave.
way down.
Unless it's just one that's yes, I mean,
Yeah.
you needed to total all the way down to 24, you got 40, so you got 9 questions.
So that's already, it's just basically starting you off 35%.
You got 77
Start off with that.
materials, so you ace that.
At that point. So basically, you gotta find how many more dryers you gotta have to go through. We had 18 more dryers, right? Well, so you have 18 more dryers, right? So you gotta have a percent. So you divide that by 2, and then it's 9%. Takes you down to 26%. From that 35 all the way down to 26.
So it's like a, so it'd be like a minus like on the 5?
Yeah, and then you
Feeders
multiply
would be
that
one
by
I would figure out where you were going.
I guess the 5 kVA.
Well, I don't know. I was hoping to be able to.
Electrical feeders
kind
got
of
motor,
work with you,
motors
Yeah.
but
primarily.
I might be there someday, go,
Multiply that by this.
I mean, there's really not that
well,
much.
it's better like if we're going through the work.
I didn't know
There are some calculations.
Whether you know or not,
Okay, so, did you get it though?
to make it go faster.
You basically already subtracted down, once you get it down to your 24 dryers, that's subtracted by.
You have one that had to do with.
So, basically.
Yeah.
What you're saying on here.
I saw the lady brought it in this morning, but
So you have 23 dryers, we're to subtract 1% from that 47.
yeah,
They work with.
Oh, that's big.
They got 35.
Feel like I'm close. Am I close or am I?
You've got, I mean, you're, the only one you kind of hit pretty well.
I was starting out at 15, 16.
Multiply that by
1824 is
Go across the map, subtract that from the 35%.
Yeah.
Okay.
Yeah, subtract it, we'll get out to 26%.
Not 12. Started from the fucking bottom.
That tells me you're just.
Serves her out right a little bit, go further.
You know
It's
what?
taking back, like, most of the
Stuff in
Oh, look at
Some of that stuff is pretty strong.
We all play a part.
I don't think you're missing.
Yeah.
We pay.
Oh, yeah, yeah.
All your ground.
Well, that's why like they keep trying to divide up all these licenses, like a solar license, a couple local licenses, it's like, yeah, I'm fucking and a lot of mine is like, we covered it all, why would you break that out, fuck that up?
I guess,
All the other than now, we think that, yeah.
Well, it's to reduce the cost of labor.
It's difficult.
Cause if you take everything that's gonna be equal to less, and that's why all the manufacturers say this stuff's good, LEDs, you gotta be careful, they wanna start putting LEDs now in your market. They wanna get everything in residential. I've already seen this with a lot of markets. They wanna take everything in house and make it so 50 volts or less. 50 volts or less.
Yeah,
Cause now you don't need electricity. Now you don't need $5 now, so anything. Or you install it in your building. Whatever it is. Now you just need a bunch of labor motherfuckers. Because you don't need a guy that's trained and certified, now your labor costs drops all the way down. But
key to the whole thing.
it's only $1 over spread, right? You got labor, you got materials, right? So what happens is the manufacturers of the equipment going in, the Romex, the wires, the prices or whatever, they'll hike all their prices up, they'll get the majority of that market. Until it gets so complicated, they need a trained guy to do it. It's always a fight over labor and material. That's what we're always fighting, right? Manufacturers will always.
I would rather you be busy like that though, because I mean, the guys who charge 3 hours a day are not gonna limit themselves. You can't just stay in the 3 hours a day, you're not solving it. You're just wasting 2 hours.
That's where all the basic economics on the business
So just be disciplined. Just be disciplined and do.
Remember the time when the fucking materials were so cheap as shit? Hey, Playboy, but you got to charge a lot of money because the fucking materials are cheap.
Yeah.
Michael was 250 foot of
I mean, if you haven't taken it yet, it's
I
not.
fucking remember it was like $39.
Yeah. Until you see the way they word it, a lot of this doesn't make any sense.
This 400 watt panel used to be
Every one of them is.
$200-300, you know?
It's different though, they really have
With-
done
with-
phenomenally.
the-
Talking out of the side of their
And the
neck.
range you use here, but the another one you need use it there.
I mean, it,
The range is 12.
It's more of.
you have to read every question 4 times before you really feel like you really understand what they're asking. A lot of them come back, you just, like I said, most important thing I can tell you is, don't forget the basics, right? The basics are the most important thing, because no matter what, how they ask it, it boils down to, what are they asking me to calculate? And what are the basics to get there, right? That's really all they're, I mean, they can word it however they wanna word it, just don't let them use it. I mean, it's anybody's guess, and we'll just start that, or we'll just start that November 1st, which is what, next week? So, technically, I'm expecting it to be a significant difference, because there's been some other, developments with the IAEI being sold to the ICC, or the, not the ICC, the ICC, which is the, you know, they've got a, they've got a plumbing code, they've got a mechanical code, they've got a fire code, they've got a building code, they don't have electrical code. And so the IAEI, which is the big, inspector group, that is been one of the, I guess, the most respected group of nonprofit agencies out there. Went to the, NSPA and went to the ICC and asked them both for a bid to buy them out. And then we're firing you all, we're keeping all your intellectual property, and that's our bid. Like it was a hostile, we don't really care, we don't want you. And then ICC was like, no problem, come over here, you all get to keep your jobs, you all get to keep your material, no problem, because they need that electrical piece. And so there's been some rumbling that a lot of the test questions in Texas came from the original SBCCI, which was based off the IAEI material, which then if they are now belong to the ICC, Texas, then it's not gonna be right. So I was suspecting that some of that's probably gonna be removed and change over too. So I think it's gonna be a pretty big change.
But it'll still, I mean, it'll still be, there might be some of your personal, like, things you're seeing, it might not be there, but you're still covering.
Yeah, of course stuff's gonna be there. Like I said, it's the basics, right? I was surprised at the sheer shift in the wording from the last time I took a master's test to this last one, right? I'm not gonna tell you why or how, just know that I've seen a master's test recently, and it was dramatically different wording than anything I've seen before.
For the veterans?
For the worse.
Oh,
There's nothing
But here's the thing, when I say that, it was confusing, but what bailed me out of it was just the basics, like I said, I mean, there's only so many ways to skin a cat, right? And if you know those core pieces, like the 70% for the grounding conductor, and which table you go to for which one of these parallel sets, you're gonna be fine. I mean, it's gonna take you a couple times to read the questions, cause it's like, what?
That's kind of, I had a accounting teacher that wrote the CPA test.
Yeah.
And he would write questions, and you're like, where the hell does this come? And that's all it was, is that, you know, you read the whole, if the question would be 4 sentences long, all you needed was 4 words.
Yeah.
The rest of it was all just hype.
I mean, it was all fair, don't get me wrong, I didn't see anything that I thought was unfair, right? What I saw was a lot of, why would you even come at this question from that direction? It doesn't even really, it was kind of foreign. It wasn't straight up asking you to size the grounding conductor for 41 dryers, right? It was really convoluted. At the end, that's what they wanted you to do, right? But just the way they asked you about it was not very direct. I wish I could give you a better example of it, but,
Well, I guess the answer may or may not correct just towards what you're after.
sometimes they can, right? I mean, it just depends. Like I said, the question that I started out this morning with, when I first read it, my first initial reaction to it was, okay, that's a range calculation. It's not a range calculation. It's a neutral calculation under 220.61. What it is, right? They just used the range and gave me that portion of it in a manner that made me go through and use it like a range question would, right? I still have to go through all those steps. But ultimately, they were asking for the grounding conductor for a single range and residential dwelling, which is part of that
The big problem
220.61.
with that is just like, you're time crunching somebody. At the same time you're doing that.
You're not gonna have any trouble with the time zone, man. You got more than it's like 5 minutes or something.
Separate, yeah. And there's separate, you see, pass one, the other side, you just have to take one, you
Yeah,
pass.
I ended up, on the math, I ended up with maybe 2 hours left over. I mean, that's me, I'm not saying everybody, but there's plenty of time, right? I will tell you, don't give them a minute back either, right? Don't give them back any time. So if you feel like you're done and you had 2 hours left over, go to the bathroom and you go sit down for 2 more hours, cause you're missing something. If you got 2 hours left over, you're probably going to
Finish, I had a lot of everybody else. Went through questions, I was
Yeah.
not 100% sure about it. Right on, he said yes, it's all okay.
The only thing I caution you about is like I said, when you're putting them, when you're doing that first run through, right? Especially on the code section stuff, if you felt really strong about answering it and not marking it as a first run through, meaning you felt like you really knew it, don't ever look at it. Yeah, don't look at it, because you'll basically second guess your out more, and you're second guess yourself out of that correct answer. In that sort of, now, the ones that you marked and answered, those were specifically because you weren't sure what the exact answer was, you just knew that that's not a problem for you, right? So you may change all of those, 90% of them might be a different answer by the time, and that's okay.
Yeah, you have to do that as a placeholder.
Just a placeholder, that's all it is.
Because if you don't answer, then you're not marking it, you're not putting it in the right bucket.
If you mark them and don't answer it, then you're gonna have a bunch of marked questions mixed in your unanswered group and in your group that you have answers on. So the cleanest way to do it is answer it and mark it, or blank, right? And those are the three buckets at that point. But the mark works if you put a placeholder on it, just so that it stays out of the unanswered group, if that makes sense. Yeah, I don't know, I probably marked 35 questions or something, which is quite a bit, right? But I didn't stop and try to look them up until I was done with all of them, because I mean, it's really, like I said, it will focus you on the sections in your code book where you need to be. You'll see the same table pop up, you know, across 4 or 5 different, questions, and so,
Those questions from that section, did you go to find those next questions that were relevant to those areas, or did you?
yes and no, and I'm not gonna tell you one way or the other is better for you.
It's something that's like, oh, here was the answer, and you know,
Yeah.
then you go and do it, but if you have to actually.
Yeah, I think, there were a couple of times that the answers, those questions were so close together that it was just, it was so easy to answer one time that I stayed on that table and found the other two that were pretty close.
Maybe any that just have some scrap paper.
I would have loved, and it used to be what I saw when there was scratch paper, that's exactly what I would do, is I would write down the question number. Like literally, if I knew that I was gonna have a bunch of them that come out of the table, I would literally write the question number down.
Are you gonna take the answers out?
Right on the table.
I don't. All right, let's talk about Article 220, because 220 is one of the significant, like load calculations in your code book, right?
You're talking about the,
That, your whiteboard slanted just a little bit back.
You trying to say is it my head?
It's the glare.
No, the guys,
Glare in my head.
us guys in the back are getting a terrible glare like on the board. I don't know if maybe it comes forward if the lights wouldn't hit the same way.
Turn the lights over there.
Yeah, there's no glare.
Just my head. All right. I think I look more rugged with all my injuries. Oop, sorry.
Yeah, scar right across the face.
All right, okay. So, I wanna go back and talk about Article 220 really quickly. It took me a long time to get this through my head. I'm gonna try to do this as painlessly as I can. 220. So within 220, you've got a lot of stuff going on. You've got basically the standard method of calculating residential dwellings. You've got the optional method of calculating residential dwellings. You've got the apartments, which is the multifamily stuff for the back. You've got the neutral sizing. You've got schools. You've got add-on places where you're adding on to an existing service. You've got optional kitchen equipment. You've got optional equipment or optional cooking equipment tables, and then you've got the optional method of calculating the service for electric kitchens. And so there's just a lot of stuff going on, right? The bottom line though is I want to start at the very beginning of Article 220 on page 92, is that what it is? And let's look at these partners real quick. And I want you to understand the structure of what 220 is, so that you don't accidentally use the wrong part at the wrong time. So you'll notice that part 1 is listed on the top of page 92 in the right-hand column. Part 1 just says general, so okay. What I do like is this little diagram down here at the bottom will help you understand the way some of this works. For example, you'll see that part 1 says general, right? Part 2 though says what?
Circuit load calculations.
Part 3 says,
Feeder the service load calculation.
that's the line in the sand you have to be careful of. Now, you'll also see optional feeder and service calculations in part 4, and you'll notice how the neutral loads ties between the two. In other words, we do get to a point where we split off with the standard method under part 3, the optional method under part 4, but the neutral calculations go with both of them, and then of course you see how the farm dwellings kind of fit in underneath there. Healthcare facilities, marinas and all that stuff were added in this edition, so you won't see that in the 2020. But I like the way that it's put together because it kind of gives you a visual of kind of how these parts and pieces fit. Now, part 2, if you look on page 93 in the left-hand column under 220.10, your book's going to be completely different because they really have retooled the numbering system on this one. But 220.10 in the 2023, right above that, you see part 2, branch circuit load calculation. I'm going to tell you the number 1 rule about branch circuits. Okay? Got your attention? You never derate branch circuits ever. How's that? What did I just say?
Never derate branch circuits, ever.
Ever. If I have a 20 amp circuit where I've got 20 amps for the load, I'm gonna size it with a 20 amp breaker, the number 12 wire on it, I will not derate any of it because the risk of all of that being on at the same time is pretty high, right? So when I'm sizing that 42 space panel and I've got all those 20 amp, each one of those individual branch circuit calculations by itself, individually, will always be 100%. There's no derating in a branch circuit. The risk is too high, okay? I want you to remember that. If you ever try to apply a derating factor to a branch circuit calculation, red phone's gonna ring on my desk and I'm gonna be right behind you, slap you on the back of the head, okay? It does not get derated, right? I can't risk a derating factor until I get to the feeders, right? When I'm talking about that main in that panel, then I can take the chance that not all longer be on at the same time, and that's where the derating happens, right? So if you look at part 3, which is listed there as your feeder and service load calculations, starting on part 3, which is on page 94, you'll notice that all of the tables that we looked at so far, the feeders, or the ranges, the dryers, are 2 great examples. All of those come in part 3, not in part 2, part 3, right? Don't apply derating factors to a branch circuit. They only apply when I'm doing a feeder calculation. So if the question's asking you for a branch circuit and they're telling you to derate or asking you to derate, be very careful because there is no derating in a branch circuit. It's 100%. Okay? Now, connected load is 100% of a potential calculation or nameplate, whatever, before any load derating factor has been applied, right? Well, the branch circuit can't be derated, then the branch circuit connected load and demand load are often the exact same number, correct? Right? That's the best way to keep that straight. It's really only in a feeder calculation where I really have a difference between a connected load and a demand load because I have a demand factor, but I don't apply demand factors to feeders. There you go. I want you to keep that straight. If you can keep that straight in your head, it'll make it a lot easier. There's only one time that that's not true, and we'll talk about that in a minute, but for the most part, that's the thing I really want you to understand, okay? So if I'm dealing with, any sort of kitchen equipment, ranges, dryers, both of those tables come in part 3. You'll notice that there's a table under 220.56 on page 98. I want you to mark that commercial only. So that table would only apply to equipment in a commercial kitchen. So yes, they have ranges there. Yes, they may have dryers or something of that nature, but only if it's a commercial kitchen with that table. Page 98, it's 220.56 is correct.
Table 220.56.
Yeah. The thing to remember about that particular table is that no matter what, you can't have a calculated value from the table that's less than the 2 largest connected load appliances in service. In other words, let's say that I had a 12 kW range and an 8 kW dish dryer, right? 20 kW combined those 2 biggest appliances, right? But then I've got 5 other really small appliances that are like 250 watts or 300 watt, little tiny appliances. I may have 5 of those. Well, what's going to happen to that table if I add 5 real little things to those 2 big things? I mean, I'm not really adding much to the service, but look at what I'm doing on the drawdown on the derating factor. I'm using small loads to really draw, and the risk is that I might dip below what those 2 big ones might actually have if they both kick on during lunchtime, right? So no matter what, it's either the calculated value from the table or 100% of the 2 biggest appliances, whichever is the bigger number. Okay? That's the danger of that table. You'll see that expressed if you look at one other thing I need to tell you about. Every table in your code book has a very specific number that's tied to an exact article number that has that exact same number, right? It's not a mistake that 220.15.B6, 7, or whatever is labeled that way, because that's tied to an article that has that exact same numbering system, right? In this case, this table is 220.56, right? If you go back to page 96, you'll see 220.56. Specifically, that article is what controls that table. And the last sentence there in that last paragraph is what I just got through telling you about. So you need to make sure that you don't lose sight of that rule. However, in no case shall your calculated value be less than the sum of the two largest, right? Something like that. I should read it now. 220.56. However, in no case shall the feeder or service calculated load be less than the sum of the largest two kitchen equipment loads. So, what I'm getting at, if I had a 12,000 watt range, an 8,000 watt dish dryer, and then I had a 250 watt rotisserie, 300 watt mixer, 200 watt, I don't know, booster of what, I don't know. And then give me one more. Oh, blender, yeah, margarita blender. Hell, mine would be like 2,000 watts. You kidding me? Anyway, 150 watts for a blender. Call it a smoothie blender or something. Right? You see how small? All four of these appliances here only contribute 3, 4, 5, 6, 7, 8, 9, 900 watts, right? That's a fraction of what that 8,000 watt or that 12,000 watts are. Yet the number of 4 additional appliances puts me at 6 on the table. What's the derating factor for 6? 55%, right? 65%. So I let these 4 small appliances inordinately draw me down to a 65% derating factor for the overall amount. But they're just not that big of an appliance load to begin with, right? If these 2 kick on at lunch, that's 20 kW, right? So if I add all these together and apply a 65% derating factor from the table, which is what it tells you to do, right? If there's 6 of it, 65% is what it says? Yeah?
6 or over.
Huh?
6 or over.
Okay, 6 or over.
Be under that 100%.
So I'm gonna add all those together at 65%, let's see what we get. What I have, 250, 3, 400, 900, right? Plus the, so 29 kW times 0.65, 1885. So if I calculate this up, I end up with all these added together, I end up with 29,000 watts, right? Everybody with me? At 65% from the table derating factor, that gives me a value of 18,800. If those two
You
kick
get
on
like
at lunch.
20, you get like 21.
Ooh, you
Oh,
broke
the
it.
computer. Man down.
Uh-oh,
Man down.
uh-oh.
No signal.
Um,
Oh shit, the bottom fell out.
Are you ready, bro?
Oh, that's what she said. That's what she said.
Yeah.
Oh shit.
It's a good thing the boss ain't in here, man.
I'm not the only one that can take the hit.
I mean, it's working.
Turn it off.
Okay, it's okay. Chinook sleep all the time. There goes some of that profit for a day.
Yeah.
Yeah, buy himself a money.
All right. Well, I think this is gonna work. How many times I hit myself?
It's gonna him, is that.
Come back next month, it's all duct taped up.
He won the computer, so he got thrown now. It's no, look, really.
Watch my horn flash up.
Ooh, look at that.
But this didn't come on, which is not good, but anyway, that's good enough right now, I'm okay with that, as long as, I didn't ruin it. You guys make me nervous.
What runs that computer one by one?
I don't know, but let's
It restarted, it didn't.
I did something. Crazy.
Okay,
will, yeah, auto recovered. Yeah, I think we're good. Okay, alright, so anyway, back to the, back to my, point there. That 18.8 that I have over there, as a calculated value,
It's actually worse because it's like 21,000 watts.
what is it?
It's
It's
actually
only-
21,000 watts, right?
What is?
It's 20,900. Yeah, that.
Yeah, it's like 20,000.
29,000, it's 20,900.
Oh, it's 20,900.
So
Ah, I see
that
what
number
you're
is
saying.
actually worse, yeah.
Oh, yeah, you're right. It is 900, not 9,000.
Yeah.
So 20,900 at 65%, which is even worse than 1880, I see what you're saying.
Yeah, 13,585.
Yeah, you're right, that's even, yeah, wow. That's an even stronger point to make, I guess, 13,
585.
585, thanks. Yeah, for sure, if I had a busy lunch.
Are we talking about table
That,
Melt
13.
down that copper.
220, 56, right?
For sure, so you understand what I'm saying,
Six
so
or more.
it's either the calculated value from the table or the sum of the largest two without any derivative factors. And if you look at the table, I think the first two are at 100%, right, on it anyway, so that's kind of a lead in for that, okay? Now, another note that you need to put on that table is for optional kitchen calculations, see page 101. So there are two tables that we deal with, that deal with commercial kitchen equipment. One of them is that specific table which just deals with the equipment itself, but there's also 220.88, which is a load calculation for commercial kitchens that are either not all electric or are all electric.
See page
101. It's 220.88. 220.88. So this would be just for the equipment, right? And then there's this table here, which is for the total service. This is a really weird table, okay? Probably the weirdest table in the whole code book, just the way it's designed. It's this one right there, okay? I want to point out that you know, it's got a parentheses where each one of those rows, depending on what size the service is overall, you'll notice that there's a parentheses that tells you to subtract something from whatever. And then after the parentheses, there's a plus and a number, right? That plus and the number is the leftover from the previous row above. So you don't have to do but just one row because each row has the previous row added as the last step, right? So that plus, for example, if I had a service that was 800 kVA, right? That third row there, which it says 50% of the amount over 325 plus the 172.5, that's 172,500 volt amps. And that's what I would have gotten if I would have done 325 amps worth of, or 325,000 VA of service at that row right there. I would have ended up with that number as a final, so that's the carryover in other words, right? So at 800 VA, I would take 50% of the amount over 325, so they give me a service that's rated at 800 kVA. Right? That's my connected load after I've added everything. Is that the all electric or not all electric? It's all electric. It's all electric. What happens here is that row says I'm gonna take 50% or 10%? 50% of anything over 325, right? Okay. I'm gonna take 325 from that 800 kVA, and it gets me, what is that? 74, right? So I'm gonna take half of this number right here, which is 230 and a half. 237 and a half. Remember, this is all VA, so I'm just gonna put, or kVA, so I'm gonna just put it like that, 237,500, right? VA. All right. That's the stuff that's in parentheses, and then that plus, what is it, what it is? When I did that, what I did was the first 325 kVA, if I went to the row above it and processed that row, I would end up with a value of 172,500. So basically, I'm doing the amount that was above that initial step, right? That's what that 237 and just added the two together. So I ended up with 0, 0,
what did you, in that first step, what did you minus the 325 for, out of the 800?
Because this 172,500 is what that first 325 ended up being on row two. Let's do row two, let's do row, so forget that example. Let's say I had a service that was sized at 325 KVA, right? You with me?
Yeah.
Alright, KVA. So take 325 on row two, what does it tell you?
10%.
Of what?
Over 200.
So 10% of anything over 200, so I'll subtract 200 from that, right? That gave me 125. I'm gonna take 10% of that 125,000 VA, that's gonna be 12,500 VA, right? You with me?
Plus 160.
160?
160, 10.
So that gives me 172.5, right?
Yeah.
So that carryover that you see at the end of the parentheses is literally the row above. So I'm just dealing with, in this case, if I have an 800 KVA, that 325 I subtracted because I just did it in the row above and I got the 172.5.
You're doing a percentage of the next one, but always bringing in the fact of the minimum they require for that other row on top.
So the amount that's over that row that we just did, which is the difference between 800 and 325, the 325, actually was 475, right? I took 50% of that, because that's the block that wasn't processed previously, and then I added the previous row to that amount.
Previous minimum, so that way you're not undercutting the current row required. Same as the ranges, really.
Or the
Very
dryers,
similar to the
kinda like the dryers, like or the carryover, right? You only have to pick whatever row you're ultimately, dealing with size-wise, right? So if they get, the one I'm thinking of is like 829 KVA or something, so it's really, literally the last row. And I think that's 50% of the amount over 800 KVA plus 410, is it not? Right, so I mean, it's not a hard table, when you get used to it, makes perfect sense, but it's really a weird format if you haven't really looked at it, okay?
This is for restaurants, right?
Yes, either all electric or not all electric, depending on which one they give you, so be careful, just be one call for the other, but. Any questions? Not really? Not that big a deal. All right, demand factors for receptacles supplied by general purpose branch circuits, category 1, category 2, basic care services. Thank God they added this table. You know what, let me go back. Let's talk about receptacles real quick, because I really need to talk about receptacles real quick. 220.14, well, it changed that, so it's not 14 anymore. It is now, if you look at, page 94, it's 220 it is 14, 14I, it's just, in J, it's still the same number, it's just on a different weird page. No I. So, page 94, left-hand column says receptacle outlets under I. To the left of that, put commercial, okay? What we're talking about in section I is only ever used in a non-residential dwelling occupancy, okay? So here's the deal. Receptacles, when I say the word receptacle, what I mean literally is this right here. That's a receptacle. We call that device a duplex because there are 2 outlets, 2 receptacles on one yoke, right? So be careful of that. A receptacle is specifically one place for you to plug something into your electrical apparatus.
Sorry, where are we marking the commercial line?
220.14I, page 1, page 94. Just over to the left, it's on the left-hand column, corner towards the top of the page there. Just put the word commercial to the left of that.
Receptacle outlet.
Basically, it's anything that's not residential is what it is, but for me, it's just commercial, a little easier to capitalize that. What'd you say?
It says receptacle outlet is what we're talking about.
Outlets for receptacles. Under I?
Yeah.
Yeah, it says receptacle outlets, okay.
So receptacle outlets. Yes, that's what I'm talking about. All right. So outlets for receptacles is, the word outlet, I tend to use the word outlet to describe that duplex receptacle, but that's not an outlet. The outlet's the box that the receptacle fits into, right? So be careful with your terminology, because an outlet could be a lighting outlet, it could be a fire alarm outlet, it could be a smoke outlet, it could be be a switch outlet, it could be a receptacle outlet, right? So an outlet's just the box for you to put something in, a device of some sort. The receptacle is one single place for you to plug something in, so there's two receptacles on that yoke, right?
1.8.
In the case of the calculations for these, in this case, it says that it is 180 VA for each single or multiple receptacles on each yoke or on one yoke. So it really doesn't matter if there's 1, 2, 3, I think 3 is the most I've ever seen on a single yoke. And I've only seen it on Google, I've never seen it in real life, but I mean, there's supposedly, I guess, 3 of them in one yoke. But it doesn't matter, what I'm looking at is the gang that fills. If I fill one gang, it's 180 VA, right? So it could be a single or a duplex, I'm still gonna calculate it 180 VA. And so when they give it to you on a test, they'll word it outlets for receptacles, meaning could be any configuration. So they're not actually giving you the number of receptacles, they're giving you the number of outlets that have receptacles in it. Does that make sense? And it's the number of outlets for receptacles that have 180 VA per each outlet for receptacles. Okay? All right, now it does tell you in the second part there that a single piece of equipment with multiple receptacles comprised of 4 or more can be calculated not less than 90 amps per receptacle. So what they're talking about there would be like, I don't know, like a crash cart in a hospital where I've got a pre-manufactured piece of equipment that has receptacles built into it. When and if I have something of that nature that has 4 or more receptacles built into it, then I look at, instead of by the gang, I do it by the receptacle. So that would be 90 and 90, which equals 180, right? But a single receptacle in that case would only be 90 VA. That'd be the only difference. So in the case of a crash cart where I've got them all built in from a manufacturer and I've got 4 more, then I would look at it by the receptacle. But that's a pretty rare case. And I've only known one question in the history of mankind that had anything to do with that, so we're gonna skip that and just really go with the, basically, every gang in a box that has receptacles in it is 180 VA. Okay? All right, now, dwelling units, if you look down under 220.41, God, they made this so much more complicated than it ever was before. I don't know why it has to be so crazy. And then have receptacle office built into 2 different spots too, which is stupid. That's really crazy. Yours would have been 220.14J, which is right underneath this section I. The new code book has them under 220.41, dwelling units minimum unit load. And it tells you at the top of page 94 in the right-hand column, unit loads include the following lighting and receptacle outlets, and no additional load calculations will be required. Man, it's so confusing. So down at the very bottom left-hand corner, under 220.41, it tells you that in single family, 2-family, multifamily, the minimum unit load should be not less than 3 VA per square foot. So when it comes to receptacle outlets in a residential dwelling, we don't look at the number of physical receptacle outlets that we have in that dwelling. What we look at is the square footage of the space that it comprises of. And it's the square footage times 3 VA that's used to calculate the receptacle loads in that area, okay? So in a residential dwelling unit, let's say that we had a living room, it had receptacle outlets here, 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 here. This is my dream living room, so, you know, my living room, I've got like 2. Anyway, I don't look at 1, 2, 3, 4, 5, 6, 7, 8 times 180 VA because that's not the way it works in residential dwellings. I look at the fact that this is a 10-foot by 10-foot space, which is 100 square feet. And then each one of these is times 3 VA. So I have 300 VA for the total receptacle and lighting load. And there's no way to separate the two. So I can't really tell you what the actual receptacle calculated load in a residential dwelling is because it's combined with the lights and there's no way to separate them.
Well, then everything else as far as so many receptacles on a wall for so much length, you'd have to add all those in.
No, I just look at the square footage and
Your
multiply
square
times
footage,
3.
just place them out wherever you
Yeah.
want.
Well, I mean, you still have to follow the rules as far as like where to lay the mat, absolutely, yeah. I think I misunderstood what you're asking. But when it comes to the load calculation, the number of physical receptacles, however that layout is.
And you're going by the total square footage of the home, not per room.
Correct, technically, yes. Every habitable space.
And have habitable space,
Yeah.
not the garage. Or
So,
enclosed.
but my point is that there's receptacles, it does matter if it's in a commercial building versus a residential building, because there are two different ways of looking at the numbers, right? In a commercial building, every single outlet for receptacles has a value, and that's how I do it. I'm gonna count up the receptacle outlets. Each one of those is 180 VA, that's gonna be my Brent circuit calculation as far as it goes. When it comes to residential dwellings, it's the square footage times 3 VA in a lump sum, but I also get the lighting included with that, so it's not just the receptacles, it's the receptacles and lighting. Okay? There is one more caveat to that. If you look at 220.50 2A and B, which is on page 96. Before I do this, I want to point out, and it does mention 210.11C1 if you look under 220.52A. So in a residential dwelling, there are some required 20 amp circuits, right? Like literally, I have to see 20 amp breakers in my panel in the garage or wherever my distribution is, and those are for 5 specific areas. If you look on page 82, under 210.11C1, 2, 3, and 4, yep. Kitchen counters,
Refrigerator, disposal.
Kitchen counters,
Two small appliances.
yep.
Small appliances for the counter.
Bathroom,
Bathroom.
bathroom, garage.
Laundry, garage.
What page was that?
2, 3, 4, 5.
82.
What?
82. Page 82.
Right. I agree with you, 100%. It used to be just 4, because the garage was added recently, and
Yeah.
that's probably the smartest thing they ever added to the code book, because my garage has got my biggest load in my house. Got a table saw, grinders, joiners, you name it. Yeah.
Welder.
Yeah, got a welder back there too. So, but at any rate, each one of those 5 areas, I need a 20 amp, and this is a branch circuit, right? Now, I could have 4 bathrooms in a dwelling unit, and then how many receptacles would I have to have, or how many circuits would I have to have for that? 1. The requirement is just 1 branch circuit for the bathrooms, so I can share all the bathrooms on that same branch circuit.
You can get by it in one and then run it everywhere.
That's right.
Yeah.
Only for the power, not for the lighting. Same thing with the laundry, you can only serve the receptacles within that laundry room. Now, it doesn't say you can only have 1 outlet in the laundry room, it just says you can't take it outside the laundry room. So you could put 5 receptacle outlets in that laundry room if you want, no problem against that. Just it can't go out and be the receptacle in the hallway on the other side of the wall.
And the garage is propane.
So there's a receptacle required per bay, but there's only 1 branch circuit required for the garage. Right, so you, yes and no. But you're right, that's another part as far as physical layout goes. But as far as the 20 amp circuits that are required, I need to see a minimum of 5 20 amp branch circuits. 2 of those for the kitchen, 1 for the laundry, 1 for the bathroom, or bathrooms, and 1 for the garage, in that order. Now, the number of physical receptacles would be based off the layout, if there's any rules or so on and so forth, right? Okay. All right, now, when it comes to load calculations, the only one of these 5 that I care about is those. I guess they figured that bathrooms and houses with guys like me don't really have that big of a load on the service, so they don't really count it. I have to have a physical 20 amp circuit so that when they do use their hair dryer, it's big enough to handle it, but it's not as long in duration to make an impact on the feeder. So if you look under 220.52 A and B, which is where we started at just a second ago, each one of these 3 required circuits here that are listed up there, which are the 2 kitchen appliances and the 1 laundry appliance, each one of those have a load calculation of 1500 VA each as a feeder calculation. So as a receptacle calculation per se in a residential dwelling, in addition to the general purpose stuff, which is what this 3 VA is, this is the only other load allocation for circuits or for receptacle outlets in a residential dwelling, which all 3 of those together equal 4,500 VA. okay? As just a general rule of thumb. Or not general rule, under the rule under 220.52 A and B. Okay? So what did you learn here? Well, receptacle outlets in a commercial building are 180 VA per yoke. Receptacle outlets in a residential dwelling are either based off the square footage or if they're part of the required circuits or 1500 VA for each one of those circuits that are required. Make sense? Yeah, I think so. Typically what you'll see them, to kind of separate those is they'll talk about the 15 amp circuits, they'll talk about, or excuse me, the 15 amp receptacles, or the 20 amp receptacles. If they talk about the 20 amp receptacles, they're referring to the receptacles that are in the 20 amp strength circuits that we're talking about here. If they're talking about 15 amps, we're talking about general purpose items that are included in the 3DA with the lighting, so that'll help you kind of keep track of that. All right, so we talked about part one being general, we talked about part two being Brent circuit load calculations, and then we talked about the feeders starting on page 94, right, part three? So part three says feeder load service calculations. Let's talk about some commercial receptacles real quick. Let's look at this. How about I had a commercial building that was, we'll call it a restaurant. In this restaurant, I had all these receptacle outlets everywhere. So, yeah, tell me I misspelled that. They spell restaurant.
Just like that.
Just like that, exactly. All right, with, let's say we had 15 20 amp receptacles in the eating area or in the dining area, right? And they gave me 10 of them in a balcony that were rated at 15 amps. And let's say 25 in the kitchen. Some of them were GFCI, some were non-GFCI, some were 20 amps, some were 15 amps, some were dedicated, whatever. I don't really care. I only care about how many gains for receptacles do I have, and we're just gonna put kitchen outlets here. Really, it doesn't matter what the rating of it is, it doesn't matter whether it's GFCI, it doesn't matter whether it's USB, it doesn't matter whether it's whatever. It's simply, does it fill a gang in the box, and if it does, I'm gonna count it 180 VA, right? Simple as that. So it's this number, this number, and this number that I care about, none of the rest of that really even floats my skirt. So I've got 25, 35, 40, 50 outlets for receptacles.
9,000. 9,000.
Times 180 VA, is that what you did?
Yes, sir.
Came out to be 9,000 even?
Yes, sir.
All right, 9,000 VA. As a branch circuit calculation, that's my total number for my demand load on the branch circuit. There's no derating ever, because I'm not gonna derate a branch circuit, right? If there had been double this number, and there'd been 100 of them instead of this, let me just do 100, let me add 50 here, and 25 there, right? So now I've got a total of 100 receptacle outlets or receptacles. 100 and 180 VA would give you 18,000, right? So at 18,000 VA, as a branch circuit, again, my branch circuit's gonna be comprised of 18,000 volt amps. I mean, there's just no other way, it's 100% of that calculated value, right? However, there's a table, if you look on the bottom of page 95, yours is 220.44, and the 2020, y'all's is 220.47, demand factor for non-dwelling receptacle outlets. Is this a non-dwelling receptacle outlet?
Yes.
Yes.
Absolutely. So does this table apply?
Yes.
Yes.
No.
Oh, shit.
Not if it's a branch calculation, right? So this table will only apply if I'm doing what kind of calculation?
Feeder?
Feeder or service calculation, right? If they're asking for the demand on the branch circuit, that's my answer.
Yes, sir.
That table never even comes in, that never even comes into my radar. Well, that doesn't really matter. I mean, my point is, I never even make it that, but literally, I stop right here, cause I'm in branch circuit calculation, right, under 220 dot, what was it, 14 J, no I, right? That's part of part two, which is the branch circuit calculation. Now, I'm gonna use this same calculation in both the service calculation and the branch circuit, right? So I'm still gonna have this as a starting point for my service calculation. But they would have to ask me for the demand on the service before I would come over here and even bother with this table. Okay? Same exact question, same number of receptacles, same number of everything. The only difference would be if they asked me for a demand on the branch versus demand on the service, two different answers, right? So as a branch circuit, 100% of that calculated value, that connected load would be my demand load. There would be no derating of branch circuit. Make sense? So as a branch circuit, 18,000 volt amps. So they wanna know how many 20 amp circuits that would take, divided by 200, or divided by 120 volts, and times divided by 20 amps, and then tell you how many physical circuits you have to provide for it, right? As a service calculation, the table that we're looking at on page 95, the 220.47 for y'all, 220.44 for you, it's kind of a weird thing. There's a block of the first 10,000 VA of any calculated value that you can't touch. It's 100%, right? So earlier when we just had 50 and we had the 9,000 VA, even as a service calculation, we didn't even get there, right? I'd have to keep all of that 9,000, but I didn't get to the amount, the 10,000. But anything above 10 kVA, I'm allowed to take 50% of the derating. So for example, in this case right here, if this was a service calculation, I'd keep 100% of the first 10,000 VA as that 18,000. And don't lose sight of that, you're gonna subtract it, but not to get rid of it, just to kind of put it over to the side. So 100% of that's kept. And then the amount that went past that, which is the 8,000 VA above that, I'm gonna take 50% of that number. And I'm gonna put it over here with that first 10,000. So my total demand on the service after that table's been applied would be 14,000 VA, or 14 kVA. My branch circuit would be 18,000, right? My demand on my service would be 14,000. Okay, any questions on that?
Your friend said that see how many circuits it is divided by 120.
And then, so for example, in this case, we're asking for like, how many number 20 amp circuits, right? I'd have to divide it by basically 2,400 VA or 120, and then by 20, depending on whether I'm talking about 20 amp circuits or 50 amp circuits, right?
Curious, where would you use that many receptacles in a service?
There's always one in there.
In my garage.
No, I mean, I'm not saying that any of these examples make any sense, I'm just saying that's very similar to what you may see on their examples, so. Good question. I mean, in commercial building, I mean, it's not unlikely to see several hundred receptacles. I mean, we do.
We're moving into a building that's 150 square foot, 50,000 per floor. There's probably 300 desks in each one for tons of people. There's freaking receptacles at quads everywhere.
Yeah.
It's similar stuff like that with
So is
these
that
commercial
considered-
buildings.
So that's considered service, not a branch?
It's both, right? I mean, when you're laying out your branch circuits, you're gonna do them at 100% of that number, right? There won't be any derating. But when it comes to the service calculation at the end, when you go to work on Monday, do you do any commercial work?
I'm more industrial.
Industrial, okay.
Yeah, commercial, you'll get into a bunch of like commercial buildings where you have just a bunch of
Yeah.
employees and they all have their own space and receptacles.
I guess what my point is, you may not have realized, but a lot of time on the set plans, if you look on the one line diagram, you'll see the load calculations where they give you the connected load and they give you the derating factors and whatnot. I mean, and it's usually spelled out. It's based on these numbers here. You probably just never really paid that much attention to it because it's really, but that's the underpinning of what those values on those the one line diagram are based off of. But it's not uncommon to see several hundred receptacles in a commercial building, and that's the way we derate them on the surface, right? As a branch circuit, I'd take that 18,000. I mean, for example, at 18,000, if I'm doing 20 amp circuits at 120 volts, 20 amps times 120 is 2,400 VA, right? So each one of those branch circuits, so I'd take 18,000 divided by 2,400. I'd need a minimum of 8 circuits for those, because I'd have to keep 100% of that as a minimum. Actually, what I got was 7.5, and I'm always round that up, right?
100%.
So, all right, so that's what I just wanted, so receptacles are 180 VA if they're in a commercial. If they're a residential dwelling, it's either 3 VA per square foot, or if they're part of the required 3 circuits that are the 2 kitchen and laundry, then there's 1,500 VA for each one of the circuits, but it's not based off the number of receptacle outlets that are in those areas, okay? It's just 1,500 VA for the circuit that feeds that area, regardless of how many receptacles there are, okay? Somebody said, refrigerator earlier, remember refrigerator is not part of that calculation, so.
That's a,
I didn't, yeah, you didn't have to open it up, just,
I don't think those are.
Alright.
That's what, 8,000.
It used to be that we had, a separate calculation under,
brand circuit heating on, so.
for receptacles for,
It depends on how you.
RV parks, or
Set
not
it
RV
up,
parks,
if it's considered service.
I'm trying to say,
then,
short power
you
receptacles.
can use-
They added that now in this edition on page 102 under 220.120. In the 2020 edition, it would have been 555.5
Straight, yeah.
or 12, something like that.
That's why I was.
But now they've added it to page 102 as a new table. It's the exact same table that used to be, it's the exact same table that used to be in 555, but now they've added it to, the section. So it says it's a new table, it's not a new table, it's just new to this section, but basically it's the same idea. Depending on the number of receptacle outlets, you have a derating factor there listed, page 102. Shore power used to be in 555, which is this article that deals with marine shore power receptacle loads, but now it's been added here. The receptacles for category 3, category 4, patient care spaces, and then there's also, if you go back one, there's a smaller table on page 101, this 220.110.1 for receptacles in general purpose branch circuit in category 1, category 2, patient care spaces. Don't lift category 1 and category 2, category 3, category 4, messenger head. Basically, we used to use, if you look back on page, where is the man load for, if you look on page 95, right? Table 220.45 is lighting load manufacturer's table. It's a derating table for residential dwellings, which is what the first one is. Hotels and motels, and then warehouse and all others kind of listed down there. But the first three there, you'll see that in a dwelling unit, when I'm doing a load calculation, I'm gonna have to keep 100% of the first 3,000 VA, and then anything beyond that up to 120,000 VA, I'm gonna take a derating factor of 35%. So I'm gonna take a pretty steep derating factor. If you go back and look at that table that was added for on page 101, that 220.110.1, you'll notice it's very similar to how it's laid out in that table. It's the first 5,000 in this case at 100%, then from 5,001 to 10,000 is 50%, so on and so forth. So basically, we used to use the table that's .45 for receptacle outlets for hospitals. Now they've created their own specific table that had new derating factors there. And the table that you see on 220.110.2, which is on page 102, for the category 3, category 4, that's exactly the same table as you see in the 220.47, which was the non-dwelling receptacle table. So we used to use that table for certain hospitals, but it was up to the designer to allow them to pick which one of the two they wanted. Now they're specifically, if you're doing category 1 or 2, it's this table or that table. So it's nothing really new, it's just reformatted and put together page 101 and 102, okay? And that's for receptacle loads, that's not for lighting or any other types of loads, it's specifically just receptacles, okay? Farm loads, I've heard some rumors that there's some Astros have had some farm loads. I've not seen any in particular, so I'm gonna skip that. The schools are listed under 220.86. I've heard some rumors back and forth about that, but I don't have any specifics for you on it. And we'll talk about service calculations tomorrow for residential dwellings in more detail, so I'm gonna skip that. All right. The other thing I need to talk to you about for receptacles is gonna be under RV parks, which is 551.71. And so, here we go.
Here.
Well, yeah, I'll tell you, beer or weed.
Or just a combination.
I kinda wonder what they were smoking whenever they created some of this stuff, cause it does get kinda weird, but, all right. RV parks, right? Basically, we have two different kinds of calculations you might run across when it comes to RV parks. It's a physical number of outlets calculation, and then it could be a load calculation for the outlets that you have, right? So one of the two. This is weird because we don't really have anywhere else but in RV parks that I know of, that there's specifically a number of physical receptacles that you have to have, provide, or whatever. But here, basically, if it's got power, every single site, no matter what it is, in an RV park, has to have 20 amp receptacle, period. Right? No ifs, ands, or buts about it. So, it doesn't matter if it's a vehicle site, it doesn't matter if it's a washdown site, it doesn't matter if it's a tent site, it doesn't matter if it has power, it has to have a 20 amp device, right? So the way to remember that is 100% of any RV park site, 100%, no matter what type of site it is, you have to have a 20 amp receptacle if it has power. You're thinking, well, what if it didn't have power? Why would I put a 20 amp receptacle to it, right? Yeah.
Well,
I have to say that because sometimes the question will give you 100 sites, and 70 of those have power.
yeah, that's exactly what mine was, where like some of them only required the 20 amp and then some of them required both on the other, hardware spot.
If you give a question where you've got some that are non-powered, take them out. Doesn't have anything to do with it, right? That's all bottom line. And you're right to ask yourself, what would you get up to, right? So you would. All right. So powered sites. Generally, those are going to break down to either vehicle sites, maintenance sites, or some other type of parking site. Maintenance.
They're probably plugging in their Tesla.
And tent site. Yeah. So of those sites, doesn't matter what kind it is, when it comes to the 20 amps, it's 100% of each and every single one of those, okay? So if I had 100 sites that had power, I'd have to have 120 amp receptacles. Now when it comes to the other two sides of receptacle outlets, is 30 amps and 50 amps. I only look at just the vehicle sites for those two. I don't care about these, or these, or these, or these. Okay? So the other 30 and 50 are relegated to just the vehicle parking sites themselves. And of those, 70% of anything that's a vehicle site has to have 30 amp. And 40% of any new site has to have a 50 amp. There is a little 20% here. I'm just gonna skip that and not talk about it. 40% are required to have 50 amps, okay? That's the physical requirement. Tent sites, if they have power, have to have what size receptacle? 20. They're not part of the calculation for the 30 and 50s. Okay? So I had 100 sites, and of those, 70 of those sites were vehicle sites, right? 70 sites, were RV sites or RV park sites. 30 of them were just general sites. How many 20 amp receptacles would I have to have, assuming they all had power? 100. So I'd have to have 120 amps based off of that. How many 30 amps would I have to have? 49. Right? 70% of 70? I would not count anything but just RV parks themselves, right, or RV sites. So of the 100, 70 of them being RV sites, 70% of that number would have to have 30 amp. Right. So 70% of that 70 sites would be 49, right?
Yep.
Okay. And how many 50s?
40% is 70.
40% of 70, which would be 28. 28, right?
20.
So that's how you do the calculation for the physical receptacle, okay? That part's not too bad, right? Just remember as we go forward, the dedicated tent sites don't calculate with the 30s and the 70% or the 40%. Those are just the RV park sites themselves exclusively, okay? So they give you dedicated tent sites or maintenance sites or washdown sites or something of that nature, just take them out. Do 70% of the RV park sites. Now, that's the physical count or requirement. Now let's talk about the load calculation. For each one of these 20 amp sites that are RV park sites, I'm gonna have to calculate a value of 2,400 VA for each one of those. All right? If it's a maintenance or other than vehicle but not a tent site, it's also 2,400 VA. If it's a tent site, it's only 600 VA. Okay? So as a load calculation, of those 20 amps that are there, I'm gonna take 70 of them at 2400 VA, the other 30 that are general sites, as long as they're not 10 sites, those would also be 2400 VA, so I'd have 100 sites at 2400 VA. If these 30 were 10 sites, then I'd have 30 of them at 600 VA and 70 of them at 2400 VA, depending on how they word them, okay? When it comes to 30 amps, it's 3600 VA for each one of those, okay? When I calculate a site as a 30 amp site, is there any way to have a 30 amp site that doesn't have a 20 amp site, or 20 amps on it? No.
Because it's 100% required.
Right, so every 30 amp would also have a 20 amp on it, right? When I do this number here, I already have this number included, so I don't do them both, right? I'm just doing the 30 amp by itself, so don't add 3600 plus 2400 for a 30-20, it's just whatever the biggest receptacle on that side is on the calculator, okay? And then for the 50 amps, I'm gonna use 12,000. Used to be 9,000, now it's 12,000, okay? I'm getting all that from 551.73 under A, it's listed up there at the top of page 517. Now, be careful, because I only calculate the largest receptacle on a site. Once I calculate that number, I forget about the other receptacles that are on that site, right? I just asked you, is there any way for me to have a 30 amp site that didn't also have a 20 amp? And you said, no, I have to have a 20 amp on every site, so I'd have to go figure that each one of these would also be a 20 amp, right? So every 30
of them would be an additional 2400 total.
Well, here's the thing, the 50s are also stacked on top of the 30s, just like the 30s are stacked on top of the 20s. You will not have a site that is a 50 amp that doesn't also have a 30 and a 20 amp, okay? So, I want you to forget about that 70% business here, because it's not really 70%, it's 30%.
Well, yeah, then you go back to your numbers and just go 49 of those 13 amps, 28 of them would also have the stack.
What's 49 minus 28?
49.
Yeah, you got that.
21.
Alright. When I do my load calculation, I wanna be careful, I'm not thinking about it as, 100%, 70%, 40%, I'm thinking about it as 30%, 40%, am I not? Think about it like that, and you won't go wrong. If I do it any other way, it's gonna screw you up left to someday. Because you have to remember, the 50 amps are stacked on top of the other ones, right? So when I do that first 40%, I knock out 40% of the other two right off the bat, right?
Do your number, put it to the side.
That's right.
Yeah.
So it's the physical requirement is 70% and 100%, but when it comes to load calculation, the first 40% of this number here and the first 40% of this number here are knocked out when I do this 40% down here. Because they're stacked on top of each other, these are layered right on. So when I do this 4, it takes care of that whole block right there. That makes sense?
Sure.
So, for example, if I had 10 sites, right? These first 4 sites, when I do that, that takes care of that whole block, because those are already wrapped up in that same step down here. So then what I have left over really is just these
30%.
3 here, which is the 30% left over that I didn't already cover with the 40% below it. And then when I do that, that takes care of that number. So then when I'm left, that 30% left of whatever the other sites are, you see what I mean? So what I want you to do is write this down somewhere, that when you do load calculations, think about it as 30% or that, 30% or that, and 40% or that. That's a whole lot easier than trying to mix the physical requirements with the load calculation requirements. Physically, it may be 100%, 70%, 40%. Load calculation is 30, 30, 40. Any other way, I promise you will mess your mind up and you're gonna come back to this class going, wait, you still already possible. Okay? Any questions on that? No?
Okay, so, I don't know.
That's okay. Which one is
So
it?
you said 100%, I'm
Let's talk about two different, let's talk about two different things. Let's talk about two different things. Physical versus load, right? Physical load calculations is this.
Right here.
100% of all sites have to have 20 amps. 70% of only, and I should put all sites here,
70%.
only 30 amps for the RV sites only, right? And then 40% for the 50 amps, again, only the RV sites, right? So that's the physical layout, that's the rules, right? 100%, 70%, 40%. So if you're calculating the physical number of receptacle outlets, that's the way the number is worked out. If I have 100 sites, right, and they're all RV sites, let's say, then I'd have to have 120 amps, 70, 30 amps, 40, 50 amps. Right? And that's the physical layout. Alright, we're done, and we'll talk about that anymore. When it comes to calculating receptacle loads, I only calculate the largest loads on the site. So if I have 100 sites, and of those 100 sites, they're all RV sites, just like I just said. That means that physically, I might have 170 and 40, but I don't calculate them that way when it comes to load calculation. Each 50 amp site that I'm gonna calculate is gonna equal 12,000 VA. And when I do this, that takes care of the first, that takes care of a 30 and a 20 altogether, right? Cause they're later.
Yeah, cause you have to have all three of those on each one of the sites. So he's adding all that together to get rid of that first. Yeah, 40% of all three of those.
And so, just to make it easier to remember, then think about it like this, it's 40%, and when I do that, of this number of sites right here, when I do that math, 40% to 12,000, that takes care of the first 40% of this 70, which leaves me with 30% that I didn't calculate under that one. And then there are 30% of the sites that didn't have a 30 amp on them, right? They were just 20 amps only. So it's 30% of 20 amps at 2,400 VA. This is not in your code book. This is a smart way of doing it. Write that in your code book so that you can kind of follow that later on. If you try to think about it as 70, 40, and 100% when you're doing a load calculation.
Well, you're gonna get the load cut for all of that.
Absolutely, absolutely. Okay? Cause I have 100 sites, right? I have 100 sites. I'm gonna do 40 sites here. I'm gonna do 70 here, right? And I'm gonna do 100% or 100 sites here. Right? That's the way that the physical load calculations come out, or the physical receptacles themselves, right? But when I do this first 40 here at 12,000 VA, when I do that load calculation, what I've done is I've collapsed the first 40 of every one of those three in that first step. So what I have left over then is 30% here and 60% here, right?
So the missing step, I think, for me at least, is like show the breakdown of the 12,000. So if you were to break down the 20 amp VA in the 20 amp column, and you know the VA for the 30 amp, and then the VA for the 50 amp, and if you add those up, that'd be the 12. It's exactly that. You're showing the total number in that 40 up there, right? That collapses all three of those because that's additive of the 50, the 40, and the or the 50, the 30, and the 20.
What he said.
I know, man. Sorry. I'm gonna fuck that up before.
Just think about it in collapse. Like I said, this is 10, but it could be 100. Doesn't really matter. One of those could be 10 sites. Basically, as a load calculation, I only count the biggest receptacle. So even though there may be 40 physical ones here and 70 physical ones here, right?
But you're not adding.
I take the first 40 of this one and this one all together, right?
Right.
Then,
That's why it's the 12,000 volt amps.
yeah,
Right.
but the 50 would be 6,000 volt amps, and then plus the 3,600 plus
Right.
the 24, I give you a 12.
Right.
So what I want you to remember is 40%,
Right.
30%, 30%. Because that's really what you're calculating, right? Whatever the sites they give you, like if they give you 100 sites and there's this many, whatever, that's the way to collapse them. It's 30% of the sites, assuming they're all RV park sites. Now, if there are 10 sites involved, take the tent sites out, put them to the side, do the RV parks just like this, and then add 600 VA times so many tent sites to your total load calculation before you do anything else. Okay? I'll show you an example. There's one more step. Page 517 of your code book, 551.73A. You'll notice it has a derating factor for service calculation, so it's just like we did with some of the other tables, based on the number of sites that you have. These are only though RV sites, so if you have 100 sites and some of them are not RVs, then you would remove the ones that are non-RVs. So only RV sites are used on the table to choose the derating factor. Include the load calculation for any site that's not an RV site, but only use the RV site number itself to actually pick the derating factor on the table. So for example, if I were to have those 10 sites right there, right? Plus an additional 10 sites that are dedicated 10 sites. So I've got a total of 20 sites, right? 10 of them that are RV sites, 10 sites that are RV. And I've got 10 sites that are tent sites. 10 sites that are tent sites. All right, if that's not confusing enough. The way this works out is I would have to have 100 sites would have to have 20 amp receptacle, right? But the load calculation is for each one of the 20 amps that I have over here that isn't a 30 or a 50, I'd have to have a 2400 VA value added for those, right? The 20 amps over here would be based off of 600 VA for each one of the dedicated 10 sites, because that's the load calculation. So I would have 10 times 2400, oh well, hold on, let me back up. The 30 amps here would be based off of 3600 VA.
That's what we're talking about.
Right? Right, and the 50 amps would be based off of 12,000 VA. All right, so if I have 10 sites, right? 10 sites, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. All right, 10 sites, right? I'm gonna do, what's the percentage for the 50?
40.
So of the 10 sites, how many of these sites do I have to have 50 amp calculation? So this one here, this one, and this one, right? When I do those, I also have taken the first 4 of those out, right? And the first 4 of those out. So what's left over is 70 amp, of the 30 amp. I'd have to have 7 total sites that have 30 amps on there, right?
Correct.
First 4 were already stacked up, so I'd end up with 30 amp, 30 amp, and 30 amp on these 3, because that's what's left over there. And then the last 3 would be 20 amp, 20 amp, 20 amp. Does that help any? So the first 4 here would be the 12,000. The next 3 here would be, or 30% would be 3,600. And the last would be 2,400.
Okay, that's
That helps.
that's the 40, 30, 30.
Yeah.
Okay.
And then I also need to make sure that I added, right? So all together, 4 times this, 4 times this, or excuse me, 4 times this, 3 times that, 3 times that, plus the 6,000 VA is my total connected load.
Okay.
But even though I have 20 sites, when I come to do my derating factor, I'm just gonna use row 10, because I'm gonna exclude the physical site count of the tent sites from the
10,
state.
10, 12, right?
10 to 12, so it'd be 50%.
50% of whatever that total is.
Right. I will include the value for these sites here, right?
But you're gonna do the D-rate at the RV sites.
That's right.
Yeah.
Because otherwise, like I said, I'm using some very small load values to bring myself way down the table. I'd end up with another 5% derating factor for 6,000 VA, which is really an inordinate, disproportionate amount of loss for that. So we include the VA for the tent sites, but we don't include the sites from the derating factor table, okay? Whew, man. You guys need a bath after that one, or am I the only one that feels like kinda dirty after that's over? Alright. There's a bunch of other stuff about RV parks there, but most of it's just stuff that you can look up code-wise, so. Alright, what time is it here? We've got,
418.
4:18. We've got, I need to do conduit fill and, we need to do wire and casting before you go. So take a 10-minute break. When you come back, let's do wire and casting, because I really have to get that done today. If we have time, we'll pick up the conduit bill, if not, we'll do it first thing in the morning. So take a 10-minute break, I'll see you back in 10 minutes, and I'll see you back in 10 minutes. We definitely know that coffee is I've been promising you fun stuff all day, and y'all ain't seen none of it yet, have you?
Oh, man, that sounds familiar. Oh, shit, yeah.
I've been called a lot of things.
So for that problem we just did, that would be 72,000 would be your total load factor?
Yeah,
But then
somewhere,
when you-
right?
But then, but your demand factor, you would only take the
Oh, that's a new one.
66,000 times.
No, I think I'm full down, right?
Oh, not even looking at it,
So you wouldn't use the number.
You don't count the wind side, so you have a total 72,000.
You know,
Times.
It sounds exactly like you got
So this is,
33 something, 33.
48,000, this is, 36.
At least you know it.
Oh, yeah.
1080.
1080. And this is gonna be 2, 4, 6. Somewhere there. Alright, so add those together, 4810, be 58.8, plus 72. So 66K, right? Plus the 6,000 days, ended up with 72,000 DA total, right? It includes this load and those loads all together.
And so, this, I know we said, you have 10 sites, so that. Right, so you have 6,000. Okay, I missed the 0 a second.
Gotcha, so 10 times the 600 there gives me the 6,000, right?
And then you have to derate it, but.
I definitely wanna make sure though that that number is included in this,
Right.
right? But
We-
then I only use
We
these.
derate it off of this number.
That's right.
And then that'd be half. And that would get us to the 36,000.
Yeah. There's one that's got 32 sites, it's got 30 amps and 20 amps on it. 32 sites, it's got 30. Asking you for the demand load on those 32 sites, which is 3,600 amps on 32.
You can say if it's an RV site, they have by percentage, 50 amp.
So I went that route with that question at one point, and I'm confident that that's not what they're doing. They're just asking you if you had
Are they
32
giving
sites.
you this?
Yep. They're just
This is
asking
what we
you,
got.
what's the load for those 32 sites by themselves, no other concerns.
So you're just gonna do this block of 30, and then you're gonna do 27 in those 32 sites.
Yep. We're gonna do 32 sites and 3,600 VA.
Oh.
What I wasn't getting is like the
It'd be
highest
like-
one out of them and then knock out the rest, don't add those rest.
So you're saying it'd be like just like this block?
Whatever the highest
32
VA
sites,
rating
You're
is.
looking at it as.
They're saying,
They're just saying-
if they, just this site right here is 32 of
Yeah,
these.
so it's a block, yeah.
Yeah.
Gotcha.
I did the same thing you're thinking for a while, but then I physically saw that question myself, and they're just asking just for that specific portion of the load.
What I wasn't getting is it was like the highest VA and then don't worry about the lower VA, just wipe it out. I wasn't clicking.
On the one you guys are talking about, you would not factor anything other than
the highest load.
3600 volt.
Yeah, that's all they're asking you.
For right here.
That's the only way to put it.
Basically, that's right.
3600, screw the 2400.
That's right.
That's what it
That's
is.
right.
Are they telling you it's an RV site where you
That's
use
what
the
we're
fan mode or?
It is a service calculation, right? If you're talking about the demand on the service for those, that
So
portion of
there's
it, right?
There's
No,
no
I
didn't-
32 site reduction or whatever.
No, I don't remember
Yes,
taking
but-
the D-rate factor on it. But if that, I mean, I'm positive, those would all be RV park sites though, just for the record. Cause you wouldn't have to have 30 amp, if it wasn't RV site. So, I mean, if they're asking for the demand load for those 32 sites, then yeah, I'd take the D-rate factor from the row 32.
Ready? You ready to text?
But I wanna say they're asking for a community or something, like they weren't asking for the table, but, yeah, I am confident that it's just that section you're talking about. They're not trying to make a back door in the 50s and 20s. Yeah, there's a load.
I could say anything about this.
So I have a question in practicality. So, cause everybody does RV sites,
Yeah.
they just put a new lake in, same way.
Yeah, it's gonna raise it up.
And so,
I mentioned when.
I'm just gonna use West Texas. for
Remember we
example.
talked about the table about the.
And there's no trees, they just put.
Yeah, with the demand.
Yeah.
How do they use that?
So,
Every RV
So,
out there.
so remember, this is a minimum, right? If I'm doing design on RV park side, I would not use this, I'd do 100% all.
If you wanna permit a RV park plan set.
That's right.
I got you.
But
That's what they're gonna
yeah,
say you have to have.
That's the minimum what you have to
Not
have.
practicality, I'm cutting myself short, so I'm
Yeah, I
not
say
sites that I
why,
can't.
right? I
Out
get
in
it.
West Texas, they will put that 200-300
Yeah.
sites.
All year round.
18 hours.
Well, all year round.
And I would design it based off of 100%.
Oh, which one is this, 200 something, I didn't find it yet.
That's why I would just put all three of them on all of them.
Yeah, this is really not, I mean, you're not really gaining much, you know, money wise to do it this way, I mean, you're saving yourself a little bit.
so
of-
that's, you're saying that's all,
All those sites that were in
it's
there.
only used if it's
It's
concerned.
50 amp side, maybe not for more than
Yeah,
30, so almost all of
you
the
only use that if
cameras
it's
are 50
concerned,
amp.
so, you have, branch check work.
No, there's all kinds of.
How they're, you know, it's service business, any receptacles for branch check.
Yes.
It's gonna happen.
Yes.
It's gonna go to, J
I don't
Bonds.
know, I guess.
Panel.
Yeah.
All right. Go to a branch. I don't know. You know?
All got it from tab.
It's
All
got-
day long, man.
You put the 8,000, but the heat calculation right there, you put it like 8,000, because you took it at 50%.
Yeah.
But what about the 100%? What about the another one, 10,000?
So,
it's
so,
not.
the first, but the real land.
It's supposed to respect.
Necessarily,
Yeah.
that's
So you, first, so it's 180, for, no, it's 180 per receptacle, right?
Yes.
So, you gotta, say you got 100 receptacles.
So you get this 120 receptacle.
Okay, so you say you got 120 receptacles times
And you
180.
probably pay that just to park it there, just to have it parked somewhere too. You're desperate, so.
Yeah, it's- They're not recreational.
Like the rapid appreciation.
Don't tell the bank that, just tell them this is my recreational vehicle.
Yeah, I know.
So I can tell you, every time I go get an RV, man, it's like, yeah, don't say you're gonna hang out in it.
It's gonna get 1.6.
Even though everyone is.
So that's.
See, I know people that are
that's
buying
what
those
you-
like mini houses,
landlords.
setting up an RV park.
Yeah.
And renting them out like
that
mini
one
homes.
too, really, it's really all.
So it's not even your RV, it's like, dude, rent that out like a house.
Yeah, the little tiny home on wheels, the little.
Yeah, but they're RVs.
Yeah.
So they're just doing RVs now, renting them out like homes, it's fucking crazy. Lease agreements, the whole bit.
Yeah, and you see people that, I don't know how they do it,
That's
because
that's
some
all-
people with
that's
3,
all
4,
I'm
5
saying
kids, and that's
right
cool
there.
for a week,
That's what you
but
say.
for a year
Yeah,
or two.
when I moved here like 5-6 years ago, cause I like made the transition,
No,
I
that's
brought my
not-
40 footer
Yeah,
over.
but that's
dropped it,
only
I had
if it's Sir,
myself, my
which
wife,
I don't
my daughter,
understand what the
2 cats and a damn
difference is
lizard in the
between-
damn
so
thing.
for-
And let me tell you, it had 3 pop outs.
No,
and
I
the
think
question-
it's
But
only
after
the
6 months
commercial.
of us trying to figure out a place where we were gonna
Yeah.
drop,
All
and it
fees,
was,
building,
I was ready to burn
so
the
that's-
thing down.
commercial.
That's what I'm saying, you know, vacation's fine, but living in a.
Couple
So
weeks
that's-
at a
that's how
time.
that would
That's the way
utilize-
it
Or yourself on a hunting tree somewhere, no
Yeah.
problem. But man, you got like
Oh,
a
I said
family,
no.
kids,
Yeah, it's still a branch circuit.
It's so far.
or if you're the only dude and all the rest of them are women.
Yes.
Yeah.
Not
That's what
a-
Yeah.
that's what it said.
People in RVs learn really quick what you can live without.
Well, that's why we hang out outside where the extra little TV is and the burner,
Yeah.
and drink our
It's still a
beer.
branch circuit.
Stay the fuck out of
It's a
there, 'cause,
commercial.
you know.
Commercial, only for commercial.
You learn.
That's why they put that extra, that's why they stuck that extra refrigerator out there. That's where the beer, that's where the beer fridge is out there, yeah. My wife would be like, hey man, I need some room for all the rest of the food.
That's my 3. That's my 3.
I'm sorry, you know what, I'll take Monday off. You go drive around and get your equipment.
One cat is
For
big,
building
got a
too,
little hanger
you
around.
got 2 different configurations. You can use this one.
Yeah, same for like a
Fuck
year.
with everything I get done, they
Or
don't
you
care.
can use
Fill up, but-
Showers like this big, they so big. Luckily, they make shower houses with campgrounds.
Maybe one.
Those things are nasty.
Yeah.
Used to more than Asian going up to 5 and got the hammer going and have foot too, so.
Oh,
I
yeah.
don't know that problem with this book of scale. The other one, the 2020. Then we need to start again.
I know that.
Yeah.
But
Yeah, I haven't seen them put one on
There's a lot of losing happening in
I get it
those
all here.
championship games start to-
That's why I've been writing
pull
this.
us back on.
Yeah.
that'll help them too, regardless of when it is.
Sounds like Oregon, Washington.
No, you pass it, you know.
Well, like if they're.
But now I'm building general one.
Yeah.
That's true too. But I mean, those conferences do a lot of play like even if they were undefeated, like they were,
All
they were
this is
exceeded.
you gotta be there before.
Gotta be still,
Same day.
But you see those in the text.
you know.
Oh, I saw lights. I see.
Week, relatively.
I don't know, maybe I hopped this. Look at the answer, yeah, that's what I think I pay for that, see,
You're taking notes for everybody, right?
Good morning.
Oh, I've already done that.
$10 a copy, man, $10 a copy.
No problem.
She takes the best
Yeah, it started off real nice, and then I was like, chicken scratch, all the time.
Every third word you can read.
Yeah.
Yeah.
Yeah, exactly. Came out the gate strong.
You don't have anything to do. Our next big thing is dinner. Call Danny and have Danny bring us somewhere with Gary, but come home, that'd be the better trade-off, I think.
That's the latest build I just got done with. It's up. And I just picked up, it's a 23. I just got the tax stamps for this compressor and all that. That's a quad stack 60. Yeah, 762 by 39. So that's a quad stack 60 right there. The gas tubes, I took out the stock one and put it adjustable so that I can adjust it for the suppressor on there.
Yeah.
Got EOTech 3-time magnifier and that night vision. It's just, that kit right there is like $1,300. And then it has that rail on there, so you can actually get your dust going. Yeah, that's the one.
Night vision,
Not thermal?
Yeah, there you go.
No, the night vision, oh, you mean, does that EOTech?
Coworker had me, it's night vision, but it also shows.
It'll show up for the thermal dot, if you go to thermal
Yeah.
with white hot or black hot.
And he can record to his phone.
Yeah,
That way, whenever he's got it going or whatever.
so he can actually see it when he's in night vision mode?
Yeah. But also, it'll record like video, like that way, you can play it back and watch it.
Yeah, so we're saying shots and shit, you can see what's going on. Yeah, I have two scopes that are not, they're electronic ones. I'm big on electronic shit. But these two scopes I have, when I was in service, I was in a Springfield M14, which is a 308. That's what all the snipers use. So I'm more of a big bullet guy versus nothing wrong with it, but I'm a big bullet guy. When you hit the shit, you use the scope. It's done. And they're, I don't know, I just, AKs are coming back. So I just got that. That's actually what they're using in the military right now. I'd do it right now if I were you, because with all the Supreme Court turns over for a lot of the SBR shit and all that, they kind of had to back off the whole like fucking with everybody in a certain process. I put them in, paid for it, put it in my shit, and 4.5 months later, I got all of that. 5 suppressors and 2 SBRs in 4 months. Yeah, they taxed it, so they apply, and then you gotta look at the website and make sure. Oh yeah, you can't just walk around with it. So that's the AK. Now the only difference is like I bought the Max full stock for that. So I pulled that down. Yeah, so I changed that, and then I got the Surefire flashlight. That one's done. But man, the new one, if you go to the military thing, the Army got a new contract. We're not doing Colt. They are M16s. You know that? Oh, Army, we're coming into a new era. They're about 6.8. It's almost a 30 caliber bullet, right? So they're not doing 5.56 anymore, which is a 22 round. It's a high, high barrel 22 round. So they're getting ready for this. They're getting ready for some boys. And everybody else in the world uses 30 caliber. Everybody else we use 22. What about because we're just not that effective on that.
That never done it
We used to
before.
be.
Never done before till it's done.
It's not like,
So
now they're actually, SIG when they
first,
contract.
sign up.
So look that up, MCX Sphere. It's a
So
308.
before you're gonna have
It's
to
a
like.
308, but they also come in different things. So I got a Spear Light.
So people that haven't been in the
Best shooting around we ever fucking shoot. You can go to a 12,
they
they can
have
get
some-
shit at
some
300
background.
yards up the
But if
sight.
you-
I'm just telling you,
done
bar none,
in school,
Springfield.
you know, you just, 4 years and
You
you
got got that in 14?
First time getting a proposal in front of you?
Oh, yeah, sure, they are.
Yeah, that's
So,
too
is that Spear Light? So that's the Spear, so that's the military version now, right now. And that's 308, 20 round mag right there, with that 50 round barrel on there. But yeah, that's what they're gonna start issuing now as, not in a 308, in a 6.8 millimeter is what they're doing. So they just, that's drastic, if you ever use 26.8 round versus a 5.56 round, I mean, it's tripled in size now. Size of gun. It's tight, it's
He's kind of explaining though,
It's just gonna cost more money,
things
though.
for us to.
Oh, yeah, for the
in order
rounds and all that.
to get past that easily. So he's not going through everyone's.
Right, and here's that version, it's called Spear Light. So,
Yeah,
same
that's what it
thing,
is. That's what it
it's a
goes
Spear
with.
Light.
What my so something is wrong.
So,
Exactly.
so the same thing, but, so that's 5.56, collapsible stock, they don't have to use a gas, it's too big. A buffer tube, it's gone. So they have all of the nuts up in here, it's a
You know what I think?
piston
You know,
system
you're past two.
up in the front. This automatically comes with some compressors attached to it already, comes with an adjustable gas block, and with this setup, with the change of the magazine, the barrel, and the extractor piece, not the entire bolt carrier. So you have the bolt carrier has one thing, that's the fire pins. So you take that out, so there's 3 items. This platform changes over to 5.56, 7.62 by 39, so you put your AK rounds through it. And then you can also change it up to 300 rounds. And all you gotta do is buy a barrel, magazine, and that little extractor. So instead of $2,400 rifle, now you can spend probably another $600-700, and then you can just change those out on the weekend, and you can go to those other rounds.
You pass.
With suppressor.
Pretty much portion, you can use the student or you feel, okay, oh, I got it this time. Next time I do it. The next, maybe after 10 times,
Yeah,
maybe you
but,
got
couple things,
the right.
because it's short
I think you pay this guy, another guy like him.
5.56 would push the
You
bolt
invest
carrier
in 400, now the board,
where
no,
that pipe
you
is,
take
that one tube is, that's the pressure come back and it kicks back.
That's about what we're
All that drops off, all that
I
extra
think my
gas,
next step,
and dirt, right?
that's the really different.
Dumps off, right, that's why like AR.
figured out what the password was.
Always coming.
It's something that I do with.
So now the tube is here. And so when it kicks it back, it doesn't, it only like moves about that much. And so all the gas is, most of the gas is coming out here. Versus inside. So it's like nowhere near as dirty, it doesn't clog, it doesn't way better for like longevity and all that. Let's get the they got this in.
Yes, sir.
Fire alarm.
Like 10-inch,
I've never.
8-inch, 8-inch, 16 or something like that. So they got little minis. They're like this big. That's the new flavor now. And then.
See that? See that? Yeah.
That's what I got.
Me too.
So that's what that is.
What do you mean, okay?
I didn't get that version. I got
You know, shoot it, what
But see, so $2,600 and you got $1,200. I got $1,000.
I don't sell the furniture, I don't care about it. But what you always have,
So you're talking like it could be $6,000. That ain't
whatever.
super fucking effective. I can get that to $6,000.
But I mean,
Good.
Oh,
Here's the back one.
That's what I think. I pray for the police and him, whatever he talked about. He's gonna be there because that's what he calls circle. Oh, that's my house.
I feel like sometimes they take advantage of I mean, if you think about it, the NFPA is very
Huh?
going and every 3 years, we all have to trash everything we have, start all over again, you know? $154 a car, and then they pay no taxes because they're non-profit. If I did that, I'd do it for life for.
Soon as you can, take it out too.
What do you call it whenever you monopolize, no, not monopoly, it's like when you control a market.
Well, if you 100% control
Yeah.
the economy, that's a monopoly, but if there's.
What do you call it, you know, the one that does all the syndicate, no, the one that does the oil stuff, it's OPEC.
Okay, when you get to a big group.
There's something, it's not oligarchy. I mean, and it's fraud.
No, man, it's also you can control the cost.
If I printed out something that cost me $10 and sold it to you for $154.
That's called capitalism, man.
Oh.
What are you talking about? That's called good job.
Didn't pay any taxes on it.
Yeah.
Okay.
You can call it church.
The church and the NFPA. Oh my Lord.
Exactly.
Good start.
I like
Good
the way
start
you-
right
I
there.
like the way you're thinking. Let me see here, let's talk about wire and patch real quick, I'm just gonna find where I'm at here.
Whoa.
Not catching all that.
Yeah, that's just.
You saw that? Alright, earlier I said something about, the most common piece that ties everything we do together is wire, right? So I mean, if you think about it, we're wiring more than anything else, cause every component that we have, except for the wireless stuff, I guess. Is wiring, right? Is wiring. The biggest enemy we have is what? Heat, right? When you're talking about wiring capacity, you gotta be really careful, right? Because wire sitting on a shelf that's not landed on anything has zero capacity. It can't carry current unless it's connected to something, correct?
Sure.
The problem is that you can't ever lose sight of the fact that whatever you land that wire on also has a temperature rating,
Yep.
right? And if you
Oh, man.
just talk about the wiring capacity and forget about the terminal capacity, you may overheat the terminal way beyond what it was manufacturer rated for, right? So when we're talking about wiring capacity, we're not talking about wiring capacity, we're talking about the branch circuit total rating of everything connected to it. And everything in our tray, whether it's a wire nut, a wire block,
Sorry,
a
man.
mechanical lug, a peckerhead head for a motor, a breaker, every single thing that we use to terminate wire for, everything has a temperature rating. Everything does, right? Manufacturers use that as a platform to say, okay, this terminal can rate this size wire, it's the largest wire available to connect to it, and it has this amount of, Celsius degrees in Celsius worth of ampacity availability. Anything beyond that, you're overexceeding the manufacturer's, designs, right? So, first thing I want to challenge you about is that we're not talking about wire sitting on a shelf, we're talking about wire as a piece of an interconnected branch circuit, right? Think about it like the weakest link in the chain. Whatever the lowest temperature rating in the branch circuit, whatever that is, becomes the maximum temperature rating for everything connected to that branch circuit, right? So if I have one item in a branch circuit that's rated for 6 degrees Celsius, guess what that 2,000 degree rated wire now becomes? 6 degree rated Celsius, right? So that's one thing we're doing.
Wasting your money.
Waste your money. The other thing too is that, you know, if I have a 90-degree rated conductor, right, that's great, it's wonderful. But if I have a terminal rated for 6 degrees, then that 90-degree rating really is kind of pointless, right? And so a long time ago, manufacturers realized that the cost difference between a 75-degree rated terminal and a 90-degree rated terminal, the value that you get for that spinal adjustment is not worth the cost that it takes to manufacture everything to a higher 90-degree standard. So 90 degrees is really a wire terminal, temperature rating, but it's not really got any use outside of that, right? So you have to remember that even though a wire might be rated for 90 degrees, it doesn't really mean anything because very few terminals that in fact, I don't think I've ever seen a terminal professionally as an electrician that's rated more than 75 degrees Celsius, right?
I don't think they make one yet.
I don't think they do. And even if they did, everything connected to it would also be rated for 90 degrees. And so it's a losing battle, right? So I want you to remember that the 90-degree column that you're about to talk about or see here is a pretty rare beast, and you have to really understand what you're doing to use it, right? And you have to just make sure you process stuff because we're not talking about, you know, really just a wire by itself. Second thing is, when we're talking about wire ampacity, what's the number 10 rated for? What are you going for? 30 amps?
Well, 30 amps in the 60 column, the 35 in the 75 column.
Alright, so I can tell you you're full of shit. I've had a 10-3 Romex that I know good and well had 80 amps on it all day long for the last 6 weeks, right? I failed an inspection, anyway, I'm not gonna go into each one, but I know it takes about 2,000 degrees Fahrenheit to melt number 10.
Right.
You're not gonna get that at 30 amps, not even close, right? The ampacity of a number 10 is probably several hundred amps if you really want to talk about it, because
Before
that's
it's
what's
melted.
that's right, before you deform it, right, or make it a wire that's no longer a number 10. So when we're talking about wire ampacity, really what we're talking about is the stuff that's wrapped around the wire and how much heat can that stuff that's wrapped around the wire handle without breaking down, right? It's all about the insulation, is really what it is. We're not really talking about wire ampacity. When I say number 10 is rated for 30 amps, I don't mean that number 10 is only rated for 30 amps because I know it's not. But the jacket wrapped around that piece of Romex that I had that 70, 80 amps on it was cracking like wildfire whenever I took it off a week or two later because it couldn't handle that kind of heat that I had it on, right? And the dielectric principle or the insulation principles, whatever the material is wrapped around that wire, needs to be protected against excess heat. And so that's what we're really talking about. We're talking about insulation ampacity is really what we're talking about. The ability of that insulation to handle the amount of heat that we're going to put on it, right? So hopefully if you'll stop thinking about wire being rated for whatever the amps are and thinking more of the jacket and the properties of the jacket and kind of how that jacket's created and what it can handle, it'll help you understand the 60, 75, 90 degree business and help you keep it straight. I know you struggle with this because I've seen the results in the field. I mean, we really struggle with wire ampacity. I think we understand a little bit, but we don't really quite understand how the application goes. Another thing too is that we got wire ampacity, but we also have another number that we have to keep our mind on, and that's the load value that we're trying to match that up with, right? And so you can't really look at wire ampacity in a vacuum, and I think that's probably part of the problem with this code book is that it looks at it in a vacuum. And finally, the last problem is that the code's looking at it as if you did come into the office and you looked over there and saw that 500 KC mill sitting on the shelf and go, gee, wonder what we put that on today, right? In my professional career, that's never happened to me. I've never walked into the shop and seen a piece of wire and wondered what I could install it on, right? Has that ever happened to you guys? No. The code book comes from that direction, though, because they don't have any choice. They don't know what you're going to install, so they have to look at it just like that. But reality, that's hard for us to understand because that's not the way we look at things. We look at things from a load value. Calculate, like I said earlier, we kind of calculate what we know that we're going to have on that wire, and then we try to select a wire based off of that, and that's where I think it gets a little fuzzy. All right. Finally, the last thing I want to talk to you about is that when we're talking about wire ampacity, we're talking about a very specific number, right? So we're talking about the maximum ampacity that a conductor can carry given certain heating conditions and number of conductors and so on and so forth. It's very specific. Now, it may not translate that way out in the field where you may have a lot more freedom or whatever, but on this test, when we're talking about wire ampacity, we're talking about that exact number that wire is rated for, okay? So don't get too upset if it doesn't seem like it makes sense. If you'll just kind of bear with me, I think you'll kind of work through it, as we go through here. But wire capacity, breaker size, and load values, three different things. They'll have to match, right? They're three different things. When I'm doing a calculation on the test, and I'm asking about a breaker size, I mean, it's not the same thing as wire capacity. And wire capacity isn't necessarily the same thing as what my load calculations are. So you just kind of have to make sure you're reading the question and answering for you there. All right, we're gonna start with, well, there's a table on page 187, we talked about that earlier, right? 310.16, I'm so glad they relabeled that, right?
Yeah.
It was 210.16 far back as I can remember.
Yeah, and then Bravo something.
Oh, it's dot 15B16, they put less than B16 on there just so we remember what it was. It's silly, anyway, 310.16, welcome back, glad to have you. She passed out a handout to you guys, which was a copy out of my own code book. I have a lot of notes on here, but I don't expect you to write all of these notes on your own code book, and this is from my 20 edition, so it's not as new as the one you're dealing with, but pretty much the information is the same. But as we're going through here, if you could just kind of keep that out, I think you'll see that the notes and things that I'm going to tell you kind of follow that format. And, you know, if you want to put all that in your book, you're certainly welcome to, or you can just take a look at, what parts of it mean something to you. Makes sense. Now, all right, we're looking at this table. You know what, I don't even want to start here, because really where we need to start is, if wire is just one part of a branch circuit, right? It's one part of, all these different components, that are, where's my picture of my components? Right there. Every one of these has that's 250 kc, that's based off of a 75-degree rated terminal. So whatever the 75-degree column of a 250 kcmil copper conductor is, that's what that mechanical load is rated to handle wire capacity wise. The wire itself has a wiring capacity. This breaker, most breakers have a 75-degree rated terminal. I don't think that's, used to be 60 degrees was really common, but that's been a long time ago. Most of them are 75. And wire nuts have a terminal rating, Polaris blocks have a temperature rating. I mean, if it has a way to bind a wire to a screw, it's gonna have a rating of either 60, 75, or 90, right? Now, the weakest link in a chain, I don't care if this is really strong and this is really strong, if I've got a small piece of wire right there that's very weak, that's gonna be the maximum amount of pull that I can pull on that chain, right? Same thing happens to the branch circuit. Whatever that lowest temperature rating is of anything connected to it becomes the highest temperature rating for anything connected to that branch circuit. Make sense? If I have a 2,000 degree rated wire that's connected to a 75 degrees Celsius terminal, I'm only going to be able to put 75 degrees Celsius worth of ampacity on that terminal, because anything more than that is going to overheat the terminal, right? So again, weakest link in the chain, and it's all about the heat, right? When we're talking about terminating that conductor, what is that terminal rated and what is that wire rated? We need to make sure that they're both taken into concert. So, in the field, I have the ability to go look at the side of every one of these terminals and see what the rating is, right? That way I know for sure if everything on here is 75 or whatever it is. On this test, do you have that ability? No, right? So you're gonna have to kind of make some assumptions, right? So we're gonna start 110.14 C1A1. 110.14C, which is going to be on page 60. Where is it? Page 65. 110.14C1A, basically, is where we're going to start. But when it comes to wire capacity, those terminals are probably every bit as important as the actual wire capacity itself. What this says is that the temperature limitations associated with the capacity conductor should be selected and coordinated so as not to exceed the, I'm reading from page 65, left-hand column, section C, where it says temperature limitations. And it says that shall be selected and coordinated so as to not to exceed the lowest temperature rating of any connected terminal, conductor, or device. I think that pretty much sums up what I just said, right? That's really important. Now in the field, like I said, we can coordinate. But on this test, you kinda have to take what they give you. You can't add anything that they don't tell you specifically, and you certainly can't, subtract anything, so. Under number one, equipment provisions, it says, the termination provisions of equipment shall be based on, unless equipment is listed, marked otherwise, blah, blah, blah. Terminal provisions of equipment for circuits rated 100 amps or less, marked for 14 og through 1 og shall be used for only one of the following. Conductor rated for 60 degrees Celsius, right there, right? And then it does go on to say, under number 3, at the top right hand column, number 3 says conductors with higher temperature ratings if the equipment's listed and identified for the use with such conductors, right? There's your 75-degree allowance. What they're saying is, look, 60 degrees is all you got, period. That's it, that's all. In fact, that's very clear. But then they say, well, but if you have a terminal that's rated for a little bit higher, then you can coordinate that with the higher temperature rating conductor, so on and so forth, right? So in other words, if I have a 75-degree rated terminal, what they're telling me under number 3 is that I could then use a 75-degree rating for a conductor, right? All right, and then right below that it says, what about the 9-degree? It doesn't even mention 9 degrees, does it?
Nope.
9 degrees not even talked about in here because
There's
it's
no
not
termination equipment that does 90 degrees yet.
There you go. So, now I will call attention to note 4. Note 4 does say if I have a motor that's marked with a design letter B, C, or D, that's important, right? Sometimes you'll see that on the test and they'll tell you got a motor with design B, class motor. Design B, C, or D is a significant notation to me because that tells me the terminals for that motor are rated for 75 degrees Celsius, right? If I don't know that, and I have a motor, and they're asking me the size of conductor, and they don't tell me the terminal's rated for 75, or they don't tell me it's design class B, C, or D, guess what the terminals on that motor are gonna be rated for in my mind? 60, right? They're not even gonna make it to the 75 because I don't have what I need to know. So this provision here allows me to use a 75-degree terminal rating for a motor if I know it's one of these 3 design levels, right? And so if you see a test question where they tell you that it's a design class B, that may be significant, especially if you're talking about a conductor sizing for it, because that will tell you you're allowed to use a higher column for the capacity value, okay? All right, protect the terminator, right? Arnold Schwarzenegger's gonna kick your butt if you don't forget to look at what is that terminal rated at. Now, the terminal rating is really the last part of the question, right? When I'm doing a calculation, I wanna start with the highest value I can, but when I'm done, I need to make sure that I don't exceed either the 60 or the 75-degree column, and I'll explain that in a little bit more detail. But just as a recap, what this is saying is that if I have a wire rated as a 14 gauge through a number 1, basically every single one of your small branch circuit conductors are included in that swap, right? Anything 1 aught or bigger, I have a parallel, that's feeder level at that point, if you ask me. They're telling me the 60-degree column is really where I'm stuck, unless I know otherwise, right? That's exactly what this says. Now, section B right below that number 4 up there says terminating provision for equipment or circuits rated over 100 amps or for conductors larger than 1 og shall be used for one of the following, and there's your 75 degrees Celsius. So here's the thing you gotta remember. When we're talking about wiring capacity, you've got to remember you have a terminal rating that you have to keep in mind at the end of the calculation. So the wiring capacity is not by itself just the only item that we're looking at. What this is telling me is anything that's size 14 og through a number 1, or 100 amps or less, right? The code book is telling me I have to consider that to be what rating? 60 degrees Celsius. That's a lot of wire. Is it not? Basically everything. I don't get to use a 75 degree as an assumption on that test unless it is 1 aught or larger. Basically 1 aught to 2000 kcmil or 101 amps or less, or more. So that 75 degrees Celsius assumption isn't something I'm allowed to do on anything that's smaller than a 1 aught, basically. Okay. You'll notice that the way I've got this bracketed out on my chart here is I've got the 6-degree column over here with the bracket that goes all the way to number 1 because that's basically the wire size they just got through telling me, right? The value in the 60-degree column for most of those. The only one that reaches over 100 is the number 1, but it's the size and the opacity, so it's still in that bracket, right? And then I've got the, let's see, this is bracketed basically all the way to 85, because that's anything that's 100 amps or less, in the 60-degree column. But, let's see, what else is that? I guess that makes sense. What is the double action mean? Oh, I just got that note, so size 14 to number 100 amps or less. I've got it noted that that's what I'm using the 60-degree column for, so. And I'll just go Romex, let's do 60-degree column, just because of that. All right, again, nowhere in there today you can talk about the 9-degree terminal rating, wasn't even mentioned. So basically I'm gonna go back to page 187 now, we're gonna look at page 187. In the 9-degree column, the note that I wrote to myself in black, and I even underlined it in red, I said must derate this column, right? And that's really, if you stop and think about it, that's the only reason why this 9-degree column even exists. It's just when I have derating effects to take into account, I'm going to try to use the biggest number I can so it doesn't hurt as bad. But that's it. It's not a standalone value. Just to the left of that, I've got a red line drawn to the right of the 75-degree column. If you think about it, if 75 degrees Celsius is the highest temperature rating you'll ever see on a terminal, well, what becomes the highest ampacity of any conductor after it's all said and done, period? A 75-degree value. So that red line on the right side of that 75-degree value is an absolute do not cross line, because at the end of the day, whether it's in the field or on this test, if I'm looking at an ampacity of a conductor, I shall not ever be more than that 75-degree column. Ever. Period. That red line is literally a do not cross line. Does that make sense? And that's for real. If that terminal is rated for a maximum value of this 75-degree, and that's the most I can get, I don't care about anything else, that conductor cannot be rated for more than 75-degree column. And in addition to that, this rule here told me that I also have to worry about that 60-degree column as well, just like I have to worry about the 75 for anything that's rated for 100 amps or less, or size 14 gauge all the way to a number 1. So I've really got 2 columns I have to worry about. If I don't know for a fact what the terminal's rated for, I'm stuck in this column, and this is a do not cross line if you think about it from that perspective. But nowhere does that 9-degree ever have any livable area, space, or being outside of just the load calculations if you have them derated. If you don't have load calculations, if there's no derating factors to take, that 9-degree column doesn't even exist to you, it's dead. I don't care if that wire is rated for 9 degrees or not, if you have no way to get it to that 75-degree or less value, it doesn't have any value. It's only there as a calculation, that's it, right? So that's the first thing. Second thing is you can only use a 9-degree column if the wire is rated for 9 degrees to begin with. So let's talk about the jacket real quick. On a letter or on a wire, you have these letters that mean different things. I'm sure y'all have seen XHHW, or XHWN-2. What else is common? THWN, THHW, THHN. What's the W suffix on a wire jacket? Water. Yeah, wet location, right? So if it doesn't have a W on it, can I put it in a wet location? No. If I run outside a building, inside a building, is there any way to get outside the inside a building without going to a wet location? Absolutely not. If you bury it below grade, I don't care where you bury it or what you bury it in, that's a wet. If you would run it overhead, outside, I mean, pretty much it's gonna be a wet location. So can I run THHN outside a building? No, it's not ready for wet, right? Well, I went to Home Depot because I had this circuit that I was gonna run outside and come back in. It was gonna be exposed to the weather, so it would have been in a wet location. I'm looking for some THWN, and I couldn't find anything with THHN in the entire Home Depot. I spent probably an hour looking through every spool of wire they had, and not every one was THHN. I'm like, what do I do now, right? I can't use this outside the building. And it was a nice couple of guys that worked there, and they're like, oh. It was red, put it on Mayface.
They don't know what size they are, how are they gonna know what kind of fucking wire
I know. Anyway, it was a little while later that I realized if you look at the jacket, it's actually a THHN/TWN-2/, and I was like, 3 or 4 days, it's a dual rating, but so THHN was such a common wire type for such a long time that it became a trade name, basically. And so
But on a
they used it-
THWN, you would already know that.
Well,
Why would you-
but they just use it for marketing purposes, really, is what it is. So it's marked as THHN, but that's really not what it is, I guess, anymore. But anyway, the first letter in a jacket, the T stands for thermoplastic. So the T is basically a PVC that's flexible and can handle some heat, right? So that's thermoplastic is what the T stands for, thermoplastic. If you see an R in a jacket, that means it's rubber or rubberized compound. If you see an X, that's some kind of a synthetic blend. And I don't think all the X's are the same synthetic blend. I don't think they're necessarily a mix of just those two compounds. I think it's simple stuff's got some other things in it, silicone or something that's, makes you feel like you're touching something wet. But at any rate, the X just is a synthetic blend of different proprietary compounds. If you see an H in the jacket, that H stands for heat rated. Well, what does heat rated mean to a manufacturer?
75 degrees.
75 degrees. A single H means that wire is rated for 75 degrees Celsius. So a THW, for example, is a thermoplastic, 75 degree rated, allowable wet conductor. You can put it in wet location, right? THWN, the N stands for a nylon outer cover, so it's just basically a nylon jacket. A double H means it's high heat rated. Which means 9 degrees Celsius. So if you see a double H, THHW, that means that's the 9 degree jacket, right? Well, it's under the 90 and 75, isn't it? So there's a problem with THHW, and I'm glad you pointed that out. But just before I finish this, what else am I missing here? Used to be a bunch of A, which were for asbestos type material. That's all gone, so I don't think we see any of that anymore. What else is out there? U is underground area. It's a high temperature. It's some sort of a Teflon coating or something like that. You see that real commonly with like fixture, appliance wiring and stuff like that. The Z.
You see it in some of the flexible.
And are you? Yeah, well, for high temperature flexible. Yeah. S is for silicone or something like that. No, service jack. That's service. Like your service cord, your SO, so on and so forth. I think your EV stuff has an E in it, but there's also some that are not marked like that I think have S, but those are flexible cords. Let's just stick with this for now. What he pointed out was that if you look under the 75 degree column, THHW, XHHW, and XHWN, all three of those are listed in the 75 degree column, but they're also listed in the 90 degree column. So the XHHW, for example, and the THHW, at the top of the table, you see where it says temperature rating conductor, see table 310.41. If we go back and look at that real quick and look up THHW or XHHW, 310.1, 2.41 on page 179, page 180. THHW is probably the best conductor example on page 180. It's kind of in the middle of the table, page 180. THHW is listed under two different temperature ratings. You've got 75 degree and then also a 90 degree, but to the left of that, or to the right of that, you'll notice that breakdown is based off of whether or not it's wet or dry. So a THHW is a 90 degree rated conductor, yes, but if I use it in a wet location, it automatically derates it to a 75. The -2, however, is a 90 degree rating in wet or dry. So that's the final note here, is that -2 is a 90 degree. This could matter if it's wet or dry, so that W with that is sometimes a problem. It's dual rated basically, but this is a 90 degree rating, wet or dry. Okay? So, I can find a lot about a jacket or wire insulation. Yes, sir.
What does the X mean?
Synthetic blend. Yeah, it's some sort of a compound that is either proprietary or some mix of rubberized PVC or something. All right. What was I saying? Oh yeah. So the XHHW and THHW, those two plus the XHWN, those three conductors, because they're listed under both the 90 and the 75, you have to be careful with those because you can put them in a wet location, but if you do, it automatically dumps them to a 75-degree starting point, right? And so that's what my notes there are talking about or trying to indicate to you with those. All right. You'll notice you go back to page 187, you have the three columns on the left-hand side, which are going to be the copper. You also have three columns on the right-hand side. You have the wire ampacity sizes, the wire sizes listed on both the left and the right. So you can read this table either right, backwards, or right, left, or right. Remember, if you're reading them right, left or right like you normally do on the copper side, the 6-degree column is the first column, 75, but on the 9-degree column, or on the aluminum side, it's backwards. So if you're reading it from left to right, or excuse me, right to left, remember your columns are reversed temperature-wise. So your first column might be the 6-degree column, it's going to be the 9-degree column. And you'd think that wouldn't need to be said, but believe it or not, I've made that mistake of trying to go backwards, and you're just used to the first column being the 6-degree column, right? But not if you're reading it from the other side, all right? You guys know where the NFPA's offices are located? The guys who wrote this code book, the ones that actually made this table right here, you know where their offices are? Quincy, Massachusetts. I don't know about you guys, but probably up there, they don't have the same temperatures we have down here in Dallas, Houston, Austin. What was it, what was the highest temperature this year? Something crazy, like I never thought in my life I'd ever hear that temperature. It was over 110. I don't remember exactly what it was, but it blew my mind. It's like, I remember when I was a kid, 101 degrees was, that was a blazing hot day. 112, 113 degrees?
Plus the humidity?
Oh my God. I don't know what they live through up there, but I guarantee you they don't live through summers like we do, right? Ambient temperature is kind of it's like a blanket, right? If I have a wire that needs to air out and try to kind of derail or trying to let some of that heat dissipate, if I put that in an oven, it's not going to dissipate very easy, is it? Every single value on this table was written by a guy that thinks 86 degrees Fahrenheit is a hot summer day. 86 degrees Fahrenheit. 86 degrees Fahrenheit to me is sitting on the porch sipping tea and enjoying my cool day, right? But to them, 86 degrees Fahrenheit, if you look at the bottom here under note number 1, it says, should be reference from passage correction factors where the ambient temperature is other than 86 degrees Fahrenheit. Well, guess what? Welcome to Texas. Basically, every single time you reference this table, you're working in ambient temperature other than 86 degrees Fahrenheit. Wet bulb temperature established for Dallas is 98 degrees Fahrenheit. I don't know if you guys knew that or not. 99 for, no, I'm sorry, 97. It's 98 for Austin, 99 for Houston. At least it was a few years back. Maybe 101 now, depending on what they redo it. But every few years, it's based off the handbook fundamentals, which is an ASHRAE standard. They take the wet bulb temperatures of all the different major airports, and that's what they use as the temperature rating to use in different sections of the country. So for us, 98, 99 degrees, which is way far more than 86 degrees Fahrenheit, is really common, right? In fact, that would be the number, especially if you're doing an outside installation. So if you're ever using this table in Texas, you should remember this table must be derated because we just don't have the temperature of 86 degrees Fahrenheit like they do up in Massachusetts, right? All right, so just bear that in mind. How do you deal with that? Well, let's say we were looking at a conductor. Let's say we're looking at a 250 kc mil XHHW, right? So 250 kc mil XHHW. All right, so that is a 9-degree rated conductor, right? It's a dual rated conductor, but it is a 9-degree rated conductor. Now, if I put it in a dry location, which that, I think the notes that I have at the top, I put, wet and dry above the 90 and 70 degree, 75-degree column, and that's what I mean by that. If it's in a 75-degree column, or excuse me, if it's in a wet location, it's rated for 75, so I put the word wet above 75, didn't I?
Yes.
And dry above the 90?
Yes.
Alright, so if that conductor is put in a dry location, that is rated then for 90 degrees Celsius. That's what it does. Okay. If I put it in a wet location, it's not rated for 90 degrees, it's rated for 75. And so that makes a difference for me, because I'm trying to figure out what's the ampacity of this 250 kcmil conductor. Well, if I look here, in the 90-degree column, I have either 290 amps or 255 amps, one of those two choices, right, as a starting point. And remember, never, ever give an answer on any test or in the field that's higher than 255 amps, right? At the end of the day, no matter what, I need to be at or below that 255, okay? I'll say it one more time. A 75-degree column is the de facto maximum temperature of ampacity of any conductor, just based off the termination itself, right? All right, so I'm gonna look at this 250 kcmil, and I'm looking at the fact that I've got an ambient temperature of 98 degrees, all right? Now, they'll usually express that in Fahrenheit, so don't let that confuse you with the 9-degree Celsius rating, the 75 degrees Celsius rating of the actual insulation. But we're looking at that XHHW, and I'm going, okay, do I start with 290 amps, or do I start with 255 amps? And the answer to that is, the 3 questions are at the bottom of that page that I gave you. I ask myself these same 3 questions every single time I do any wiring capacity, even to this day, because those are my 3 filters, right? And I need to make sure that I'm clear on the answer to those, because number 1, do I have a wire rated for 9 degrees to begin with? Yeah, I do. As a matter of fact, the double H in that jacket does mean it's rated for 9 degrees, so far so good. Now, in the case of the dual rated conductors, my next question is going to be, is it wet or dry? Is that the next one, or do I ask you for the, do I have derating factors to apply? I didn't have derating factors here because I didn't have anything written just but that, but the minute I wrote that derating factor right there is the math that I'm talking about. So yes, I've got derating factors to apply. I have a way to get from that 9-degree column of 290 amps down to at least a 255 or less. So yes to that answer, and the next question is going to be, do I have a wet or dry location for dual rated conductors? In this case, yeah, I've got a dry location. So I'm good. All 3 of those gave me a yes answer. That means that I'm going to start with the highest value of that capacity of that conductor as I possibly can, which in this case comes out of the 9-degree Celsius column and is rated at 290 amps. Everybody with me so far? Okay, so far so good. Now, I've got a 98 degrees Fahrenheit, so how do I adjust for that? If I go back 2 pages to page 185, you have to be careful at page 185 because there's 2 tables. So the table on the top of the page is the table that matches with where we just came from. The one on the bottom, put an X to it because it has to do with a totally different table that has to do with, I think, outdoor suspended air conductor or something like that. That's certainly not what we normally do. So the bigger table at the bottom of the page, exit out with your highlighter. You don't want to use it. The smaller table at the top on page 185, table 31015B11. What? B11, really? Okay, well, that's what it is, B11. Is the table we're talking about. Now, you'll notice that this table has the Fahrenheit at the far right and the Celsius temperature on the far left. That's the ambient temperature they're talking about. In our case, most of the time, if they're going to give it to us, they're going to express it in Fahrenheit. So I'm looking at where does that 98 degrees Fahrenheit fall at on the table. So we're on the right-hand column. Well, I see it falls between the 96 and 104 row, right? So that's the row that we're on. And now I look to the left, I've got 3 temperature values. I got 91, 88, or 82, based off of 90, 75, and 60. Whatever column I take this value off of on the other page, 187, I need to make sure I stay in that same temperature rating column. So in the case of, in case, I saw it coming too, I was like, all right.
That's a
Good catch though.
look,
It's,
that's my minute. Yeah, freaking minutes.
Yes, sir. So, because I took the 9-degree column
sé
off the,
jodido el video.
the 290 off the 9-degree column on the page, I'm gonna stay on that column here. So 96 to 104 Fahrenheit, I'm giving you a 91%.
How do they have us connected?
So I'm gonna take a 91% derating factor against that 290 amps, because that temperature is 90 degrees Fahrenheit, would give you that. All right, so what does that come up to? 290 times 0.91.
How is this connected?
263.9. So I end up with a value of 263.9. All right, so on the test,
Yep.
they're gonna give me 264.
I got this.
They're gonna give me 263, 290, 255. What's the correct answer for the maximum temperature of that conductor after all that's